Section 20 of The Fourth Dimension by Charles Howard Hinton. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 11. Nomenclature and Analogies Preliminary to the Study of Four-Dimensional Figures. Part 2. Taking now a different point of view, let us suppose the cubes to be presented to the plane being by being passed transverse to his plane. Let us suppose the sheet of matter over which the plane being and all objects in his world slide to be of such a nature that objects can pass through it without breaking it. Let us suppose it to be of the same nature as the film of a soap bubble, so that it closes around objects pushed through it, and however the object alters its shape as it passes through it, let us suppose this film to run up to the contour of the object in every part, maintaining its plane surface unbroken. Then we can push a cube or any object through the film, and the plane being who slips about in the film will know the contour of the cube just and exactly where the film meets it. Figure 90 represents a cube passing through a plane film. The plane being now comes into contact with a very thin slice of the cube, somewhere between the left and right hand faces. This very thin slice he thinks of as having no thickness, and consequently his idea of it is what we call a section. It is bounded by him by pink lines front and back, coming from the part of the pink face he is in contact with, and above and below by light yellow lines. Its corners are not null-coloured points, but white points, and its interior is ochre, the colour of the interior of the cube. If now we suppose the cube to be an inch in each dimension, and to pass across from right to left through the plane, then we should explain the appearances presented to the plane being by saying, first of all, you have the face of a cube. This lasts only a moment. Then you have a figure of the same shape, but differently coloured. This, which appears not to move to you in any direction which you know of, is really moving transverse to your plane world. Its appearance is unaltered, but each moment it is something different, a section further on in the white, the unknown dimension. Finally, at the end of the minute, a face comes in exactly like the face you first saw. This finishes up the cube. It is the further face in the unknown dimension. The white line, which extends in length just like the red or the yellow, you do not see as extensive. You apprehend it simply as an enduring white point. The null point, under the condition of movement of the cube, vanishes in a moment. The lasting white point is really your apprehension of a white line running in the unknown dimension. In the same way, the red line of the face by which the cube is first in contact with the plane lasts only a moment. It is succeeded by the pink line, and this pink line lasts for the inside of a minute. This lasting pink line is your apprehension of a surface which extends in two dimensions just like the orange surface extends, as you know it, when the cube is at rest. But the plane creature might answer, this orange object is substance, solid substance, bounded completely and on every side. Here, of course, the difficulty comes in. His solid is our surface. His notion of a solid is our notion of an abstract surface with no thickness at all. We should have to explain to him that from every point of what he called a solid, a new dimension runs away. From every point a line can be drawn in a direction unknown to him, and there is a solidity of a kind greater than that which he knows. This solidity can only be realized by him by his supposing an unknown direction, by motion in which what he conceives to be solid matter instantly disappears. The higher solid, however, which extends in this dimension as well as in those which he knows, lasts when a motion of that kind takes place. Different sections of it come consecutively in the plane of his apprehension, and take the place of the solid which he at first conceives to be all. Thus the higher solid, our solid in contradistinction to his area solid, his two-dimensional solid, must be conceived by him as something which has duration in it, under circumstances in which his matter disappears out of his world. We may put the matter thus, using the conception of motion. A null point moving in a direction away generates a yellow line, and the yellow line ends in a null point. We suppose, that is, a point to move and mark out the products of this motion in such a manner. Now suppose this whole line, as thus produced, to move in an upward direction. It traces out the two-dimensional solid, and the plane being gets an orange square. The null point moves in a red line and ends in a null point. The yellow line moves and generates an orange square and ends in a yellow line. The farther null point generates a red line and ends in a null point. Thus, by movement in two successive directions known to him, he can imagine his two-dimensional solid produced with all its boundaries. Now we tell him this whole two-dimensional solid can move in a third or unknown dimension to you. The null point, moving in this dimension out of your world, generates a white line and ends in a null point. The yellow line moving generates a light yellow two-dimensional solid and ends in a yellow line. And this two-dimensional solid, lying end on to your plane world, is bounded on the far side by the other yellow line. In the same way, each of the lines surrounding your square traces out an area, just like the orange area you know. But there is something new produced, something which you had no idea of before. It is that which is produced by the movement of the orange square. That, than which you can imagine nothing more solid, itself moves in a direction open to it, and produces a three-dimensional solid. Using the addition of white to symbolize the products of this motion, this new kind of solid will be light orange or ochre, and it will be bounded on the far side by the final position of the orange square which traced it out, and this final position we suppose to be coloured like the square in its first position, orange with yellow and red boundaries and null corners. This product of movement, which is so easy for us to describe, would be difficult for him to conceive, but this difficulty is connected rather with its totality than with any particular part of it. Any line or plane of this, to him higher, solid, we could show to him and put in his sensible world. We have already seen how the pink square could be put in his world by a turning of the cube about the red line, and any section which we can conceive made of the cube could be exhibited to him. You have simply to turn the cube and push it through, so that the plane of his existence is the plane which cuts out the given section of the cube. Then the section would appear to him as a solid. In his world he would see the contour, get to any part of it by digging down into it. The process by which a plane being would gain a notion of a solid. If we suppose the plane being to have a general idea of the existence of a higher solid, our solid, we must next trace out in detail the method, the discipline, by which he would acquire a working familiarity with our space existence. The process begins with an adequate realization of a simple solid figure. For this purpose we will suppose 8 cubes forming a larger cube, and first we will suppose each cube to be coloured throughout uniformly. Let the cubes in figure 91 be the 8, making a larger cube. Now, although each cube is supposed to be coloured entirely through with the colour, the name of which is written on it, still we can speak of the faces, edges and corners of each cube, as if the colour scheme we have investigated held for it. Thus, on the null cube we can speak of a null point, a red line, a white line, a pink face, and so on. These colour designations are shown on number 1 of the views of the tesseract in the plate. Reader's note. This refers to a colour plate headed Views of the Tesseract in the original volume. The scan of the volume on archive.org includes a black and white representation of it. This is included in the illustration file which accompanies this recording. End reader's note. Here these colour names are used simply in their geometrical significance. They denote what the particular line, etc., referred to would have as its colour, if in reference to the particular cube the colour scheme described previously were carried out. If such a block of cubes were put against the plane and then passed through it from right to left at the rate of an inch a minute, each cube being an inch each way, the plane being would have the following appearances. First of all, 4 squares, null, yellow, red, orange, lasting each a minute, and secondly, taking the exact places of these 4 squares, 4 others, coloured white, light yellow, pink, ochre. Thus, to make a catalogue of the solid body, he would have to put side by side in his world 2 sets of 4 squares each, as in figure 92. The first are supposed to last a minute, and then the others to come in place of them, and also last a minute. In speaking of them, he would have to denote what part of the respective cube each square represents. Thus, at the beginning, he would have null cube, orange face, and after the motion had begun, he would have null cube, ochre section. As he could get the same coloured section whichever way the cube passed through, it would be best for him to call this section white section, meaning that it is transverse to the white axis. These colour names, of course, are merely used as names, and do not imply in this case that the object is really coloured. Finally, after a minute, as the first cube was passing beyond his plane, he would have null cube, orange face again. The same names will hold for each of the other cubes, describing what face or section of them the plane being has before him, and the second wall of cubes will come on, continue, and go out in the same manner. In the area he thus has, he can represent any movement which we carry out in the cubes, as long as it does not involve a motion in the direction of the white axis. The relation of parts that succeed one another in the direction of the white axis is realized by him as a consecution of states. Now, his means of developing his space apprehension lies in this, that which is represented as a time sequence in one position of the cubes can become a real coexistence if something that has a real coexistence becomes a time sequence. We must suppose the cubes turned round each of the axes, the red line and the yellow line. Then something which was given as time before will now be given as the plane creature's space. Something which was given as space before will now be given as a time series as the cube is passed through the plane. The 3 positions in which the cubes must be studied are the ones given above and the 2 following ones. In each case, the original null point, which was nearest to us at first, is marked by an asterisk. In figures 93 and 94, the point marked with a star is the same in the cubes and in the plane view. In figure 93, the cube is swung round the red line so as to point towards us, and consequently the pink face comes next to the plane. As it passes through, there are 2 varieties of appearance, designated by the figures 1 and 2 in the plane. These appearances are named in the figure and are determined by the order in which the cubes come in the motion of the whole block through the plane. With regard to these squares severally, however, different names must be used, determined by their relations in the block. Thus, in figure 93, when the cube first rests against the plane, the null cube is in contact by its pink face. As the block passes through, we get an ochre section of the null cube, but this is better called a yellow section, as it is made by a plane perpendicular to the yellow line. When the null cube has passed through the plane, as it is leaving it, we get again a pink face. The same series of changes take place with the cube appearances which follow on those of the null cube. In this motion the yellow cube follows on the null cube, and the square marked yellow in 2 in the plane will be first yellow pink face, then yellow yellow section, then yellow pink face. In figure 94, in which the cube is turned about the yellow line, we have a certain difficulty, for the plane being will find that the position his squares are to be placed in will lie below that which they first occupied. They will come where the support was on which he stood his first set of squares. He will get over this difficulty by moving his support. Then, since the cubes come upon his plane by the light yellow face, he will have, taking the null cube as before for an example, null, light yellow face, null, red section, because the section is perpendicular to the red line, and finally, as the null cube leaves the plane, null, light yellow face. Then, in this case, red following on null, he will have the same series of views of the red as he had of the null cube. There is another set of considerations which we will briefly allude to. Suppose there is a hollow cube, and a string is stretched across it from null to null, R, Y, WH, as we may call the far diagonal point. How will this string appear to the plane being as the cube moves transverse to his plane? Let us represent the cube as a number of sections, say 5, corresponding to 4 equal divisions made along the white line perpendicular to it. Reader's note. See figure 95. End reader's note. We number these sections 0, 1, 2, 3, 4, corresponding to the distances along the white line at which they are taken, and imagine each section to come in successively, taking the place of the preceding one. These sections appear to the plane being, counting from the first, to exactly coincide each with the preceding one, but the section of the string occupies a different place in each to that which it does in the preceding section. The section of the string appears in the position marked by the dots. Hence, the slant of the string appears as a motion in the framework marked out by the cube sides. If we suppose the motion of the cube not to be recognized, then the string appears to the plane being as a moving point. Hence, extension on the unknown dimension appears as duration. Extension sloping in the unknown direction appears as continuous movement. End of section 20. Section 21 of The Fourth Dimension by Charles Howard Hinton. This LibriVox recording is in the public domain, recording by Peter Yearsley. Chapter 12. The Simplest Four-Dimensional Solid. A plane being, in learning to apprehend solid existence, must first of all realize that there is a sense of direction altogether wanting to him. That which we call right and left does not exist in his perception. He must assume a movement in a direction and a distinction of positive and negative in that direction, which has no reality corresponding to it in the movements he can make. This direction, this new dimension, he can only make sensible to himself by bringing in time, and supposing that changes which take place in time are due to objects of a definite configuration in 3 dimensions passing transverse to his plane, and the different sections of it being apprehended as changes of one and the same plane figure. He must also acquire a distinct notion about his plane world. He must no longer believe that it is the all of space, but that space extends on both sides of it. In order, then, to prevent his moving off in this unknown direction, he must assume a sheet, an extended solid sheet in 2 dimensions, against which, in contact with which, all his movements take place. When we come to think of a 4-dimensional solid, what are the corresponding assumptions which we must make? We must suppose a sense which we have not, a sense of direction wanting in us, something which a being in a 4-dimensional world has, and which we have not. It is a sense corresponding to a new space direction, a direction which extends positively and negatively from every point of our space, and which goes right away from any space direction we know of. The perpendicular to a plane is perpendicular not only to 2 lines in it, but to every line, and so we must conceive this fourth dimension as running perpendicularly to each and every line we can draw in our space. And as the plane being had to suppose something which prevented his moving off in the third, the unknown dimension to him, so we have to suppose something which prevents us moving off in the direction unknown to us. This something, since we must be in contact with it in every one of our movements, must not be a plane surface, but a solid. It must be a solid which in every one of our movements we are against, not in. It must be supposed as stretching out in every space dimension that we know, but we are not in it, we are against it, we are next to it in the fourth dimension. That is, as the plane being conceives himself as having a very small thickness in the third dimension, of which he is not aware in his sense experience, so we must suppose ourselves as having a very small thickness in the fourth dimension, and being thus fourth dimensional beings, to be prevented from realizing that we are such beings by a constraint which keeps us always in contact with a vast solid sheet which stretches on in every direction. We are against that sheet, so that if we had the power of four-dimensional movement, we should either go away from it or through it, all our space movements as we know them being such that, performing them, we keep in contact with this solid sheet. Now, consider the exposition a plane being would make for himself as to the question of the enclosure of a square and of a cube. He would say the square, A, in figure 96, is completely enclosed by the four squares A far, A near, A above, A below, or, as they are written, AN, AF, AA, AB. If now he conceives the square A to move in the, to him, unknown dimension, it will trace out a cube, and the bounding squares will form cubes. Will these completely surround the cube generated by A? No, there will be two faces of the cube made by A left uncovered. The first, that face which coincides with the square A in its first position, the next, that which coincides with the square A in its final position. Against these two faces, cubes must be placed in order to completely enclose the cube A. These may be called the cubes left and right, or AL and AR. Thus each of the enclosing squares of the square A becomes a cube, and two more cubes are wanted to enclose the cube formed by the movement of A in the third dimension. The plane being could not see the square A with the squares AN, AF, etc. placed about it, because they completely hide it from view, and so we, in the analogous case in our three-dimensional world, cannot see a cube A surrounded by six other cubes. These cubes we will call A near, AN, A far, AF, A above, AA, A below, AB, A left, AL, A right, AR, shown in figure 97. If now the cube A moves in the fourth dimension right out of space, it traces out a higher cube, a tesseract as it may be called. Each of the six surrounding cubes carried on in the same motion will make a tesseract also, and these will be grouped around the tesseract formed by A. But will they enclose it completely? All the cubes, AN, AF, etc., lie in our space, but there is nothing between the cube A and that solid sheet in contact with which every particle of matter is. When the cube A moves in the fourth direction, it starts from its position, say AK, and ends in a final position, AN. Note, using the words ana and kata for up and down in the fourth dimension. End note. Now the movement in this fourth dimension is not bounded by any of the cubes AN, AF, nor by what they form when thus moved. The tesseract which A becomes is bounded in the positive and negative ways in this new direction by the first position of A and the last position of A. Or, if we ask how many tesseracts lie around the tesseract which A forms, there are 8, of which one meets it by the cube A, and another meets it by a cube like A at the end of its motion. We come here to a very curious thing. The whole solid cube A is to be looked on merely as a boundary of the tesseract. Yet this is exactly analogous to what the plane being would come to in his study of the solid world. The square A, figure 96, which the plane being looks on as a solid existence in his plane world, is merely the boundary of the cube, which he supposes generated by its motion. The fact is that we have to recognise that if there is another dimension of space, our present idea of a solid body, as one which has 3 dimensions only, does not correspond to anything real, but is the abstract idea of a 3-dimensional boundary limiting a 4-dimensional solid, which a 4-dimensional being would form. The plane being's thought of a square is not the thought of what we should call a possibly existing real square, but the thought of an abstract boundary, the face of a cube. Let us now take our 8 coloured cubes, which form a cube in space, and ask what additions we must make to them to represent the simplest collection of 4-dimensional bodies, namely a group of them of the same extent in every direction. In plane space we have 4 squares, in solid space we have 8 cubes, so we should expect in 4-dimensional space to have 16 4-dimensional bodies, bodies which in 4-dimensional space correspond to cubes in 3-dimensional space, and these bodies we call tesseracts. Given then the null, white, red, yellow cubes, and those which make up the block, we notice that we represent perfectly well the extension in 3 directions. Figure 98. From the null point of the null cube, travelling 1 inch, we come to the white cube. Travelling 1 inch away, we come to the yellow cube. Travelling 1 inch up, we come to the red cube. Now if there is a 4th dimension, then travelling from the same null point for 1 inch in that direction, we must come to the body lying beyond the null region. I say null region, not cube, for with the introduction of the 4th dimension, each of our cubes must become something different from cubes. If they are to have existence in the 4th dimension, they must be filled up from in this 4th dimension. Now, we will assume that as we get a transference from null to white, going in one way, from null to yellow, going in another, so going from null in the 4th direction, we have a transference from null to blue, using thus the colours white, yellow, red, blue, to denote transferences in each of the 4 directions, right, away, up, unknown, or 4th dimension. Reader's note, figure 99, a plane being's representation of a block of 8 cubes by 2 sets of 4 squares. End reader's note. Hence, as the plane being must represent the solid regions he would come to by going right, as 4 squares lying in some position in his plane arbitrarily chosen, side by side with his original 4 squares, so we must represent those 8 4-dimensional regions which we should come to by going in the 4th dimension from each of our 8 cubes, by 8 cubes placed in some arbitrary position relative to our first 8 cubes. Reader's note, figure 100, end reader's note, our representation of a block of 16 tesseracts by 2 blocks of 8 cubes. Footnote, the 8 cubes used here in 2 can be found in the second of the model blocks. They can be taken out and used. End footnote. Hence, of the 2 sets of 8 cubes, each one will serve us as a representation of one of the 16 tesseracts which form one single block in 4-dimensional space. Each cube, as we have it, is a tray, as it were, against which the real four-dimensional figure rests, just as each of the squares which the plane being has is a tray, so to speak, against which the cube it represents could rest. If we suppose the cubes to be 1 inch each way, then the original 8 cubes will give 8 tesseracts of the same colours, or the cubes extending each 1 inch in the fourth dimension. But after these there come, going on in the fourth dimension, 8 other bodies, 8 other tesseracts. These must be there if we suppose the four-dimensional body we make up to have 2 divisions, 1 inch each in each of 4 directions. The colour we choose to designate the transference to this second region in the fourth dimension is blue. Thus, starting from the null cube and going in the fourth dimension, we first go through 1 inch of the null tesseract, then we come to a blue cube, which is the beginning of a blue tesseract. This blue tesseract stretches 1 inch farther on in the fourth dimension. Thus, beyond each of the 8 tesseracts, which are of the same colour as the cubes which are their bases, lie 8 tesseracts whose colours are derived from the colours of the first 8 by adding blue. Thus, null gives blue, yellow gives green, red gives purple, orange gives brown, white gives light blue, pink gives light purple, light yellow gives light green, ochre gives light brown. The addition of blue to yellow gives green. This is a natural supposition to make. It is also natural to suppose that blue added to red makes purple. Orange and blue can be made to give a brown by using certain shades and proportions, and ochre and blue can be made to give a light brown. But the scheme of colours is merely used for getting a definite and realizable set of names and distinctions visible to the eye. Their naturalness is apparent to anyone in the habit of using colours, and may be assumed to be justifiable, as the sole purpose is to devise a set of names which are easy to remember, and which will give us a set of colours by which diagrams may be made easy of comprehension. No scientific classification of colours has been attempted. Starting then with these 16 colour names, we have a catalogue of the 16 tesseracts which form a four-dimensional block analogous to the cubic block. But the cube which we can put in space and look at is not one of the constituent tesseracts. It is merely the beginning, the solid face, the side, the aspect of a tesseract. We will now proceed to derive a name for each region, point, edge, plane face, solid, and a face of the tesseract. The system will be clear if we look at a representation in the plane of a tesseract with 3 and one with 4 divisions in its side. The tesseract made up of 3 tesseracts each way corresponds to the cube made up of 3 cubes each way, and will give us a complete nomenclature. In this diagram, figure 101, 1 represents a cube of 27 cubes, each of which is the beginning of a tesseract. These cubes are represented simply by their lowest squares. The solid content must be understood. 2 represents the 27 cubes, which are the beginnings of the 27 tesseracts 1 inch on in the fourth dimension. These tesseracts are represented as a block of cubes put side by side with the first block, but in their proper positions they could not be in space with the first set. 3 represents 27 cubes forming a larger cube, which are the beginnings of the tesseracts which begin 2 inches in the fourth direction from our space and continue another inch. In figure 102 we have the representation of a block of 4 by 4 by 4 by 4 or 256 tesseracts. They are given in 4 consecutive sections, each supposed to be taken 1 inch apart in the fourth dimension, and so giving 4 blocks of cubes, 64 in each block. Here we see, comparing it with the figure of 81 tesseracts, that the number of the different regions shows a different tendency of increase. By taking 5 blocks of 5 divisions each way, this would become even more clear. Footnote: the coloured plate, figures 1, 2, 3, shows these relations more conspicuously. End footnote. We see, figure 102, that starting from the point at any corner, the white coloured regions only extend out in a line. The same is true for the yellow, red and blue. With regard to the latter, it should be noticed that the line of blues does not consist in regions next to each other in the drawing, but in portions which come in different cubes. The portions which lie next to one another in the fourth dimension must always be represented so when we have a three-dimensional representation. Again, those regions, such as the pink one, go on increasing in 2 dimensions. About the pink region, this is seen without going out of the cube itself. The pink regions increase in length and height, but in no other dimension. In examining these regions, it is sufficient to take one as a sample. The purple increases in the same manner, for it comes in a succession from below to above in block 2, and in a succession from block to block in 2 and 3. Now, a succession from below to above represents a continuous extension upwards, and a succession from block to block represents a continuous extension in the fourth dimension. Thus, the purple regions increase in 2 dimensions, the upward and the fourth. So, when we take a very great many divisions, and let each become very small, the purple region forms a 2-dimensional extension. In the same way, looking at the regions marked LB, or light blue, which starts nearest a corner, we see that the tesseracts occupying it increase in length from left to right, forming a line, and that there are as many lines of light blue tesseracts as there are sections between the first and last section. Hence, the light blue tesseracts increase in number in 2 ways, in the right and left, and in the fourth dimension. They ultimately form what we may call a plane surface. Now, all those regions which contain a mixture of 2 simple colours, white, yellow, red, blue, increase in 2 ways. On the other hand, those which contain a mixture of 3 colours increase in 3 ways. Take, for instance, the ochre region. This has 3 colours, white, yellow, red, and in the cube itself it increases in 3 ways. Now regard the orange region. If we add blue to this, we get a brown. The region of the brown tesseracts extends in 2 ways on the left of the second block, number 2 in the figure. It extends also from left to right in succession from one section to another, from section 2 to section 3 in our figure. Hence the brown tesseracts increase in number in 3 dimensions, upwards, to and fro, fourth dimension. Hence they form a cubic, a 3-dimensional region. This region extends up and down, near and far, and in the fourth direction, but is thin in the direction from left to right. It is a cube which, when the complete tesseract is represented in our space, appears as a series of faces on the successive cubic sections of the tesseract. Compare figure 103, in which the middle block, 2, stands as representing a great number of sections intermediate between 1 and 3. In a similar way, from the pink region, by addition of blue, we have the light purple region, which can be seen to increase in 3 ways as the number of divisions becomes greater. The 3 ways in which this region of tesseracts extends are up and down, right and left, fourth dimension. Finally, therefore, it forms a cubic mass of very small tesseracts, and when the tesseract is given in space sections, it appears on the faces containing the upward and the right and left dimensions. We get then, altogether as 3-dimensional regions, ochre, brown, light purple, light green. Finally, There is the region which corresponds to a mixture of all the colours. There is only one region such as this. It is the one that springs from ochre by the addition of blue. This colour we call light brown. Looking at the light brown region, we see that it increases in 4 ways. Hence, the tesseracts of which it is composed increase in number in each of 4 dimensions, and the shape they form does not remain thin in any of the 4 dimensions. Consequently, this region becomes the solid content of the block of tesseracts itself. It is the real 4-dimensional solid. All the other regions are then boundaries of this light brown region. If we suppose the process of increasing the number of tesseracts and diminishing their size carried on indefinitely, then the light brown coloured tesseracts become the whole interior mass. The 3-coloured tesseracts become 3-dimensional boundaries, thin in 1 dimension, and form the ochre, the brown, the light purple, the light green. The 2-coloured tesseracts become 2-dimensional boundaries, thin in 2 dimensions. For example, the pink, the green, the purple, the orange, the light blue, the light yellow. The 1-coloured tesseracts become bounding lines, thin in 3 dimensions, and the null points become bounding corners, thin in 4 dimensions. From these thin real boundaries we can pass in thought to the abstractions, points, lines, faces, solids, bounding the 4-dimensional solid, which in this case is light brown coloured, and under this supposition the light brown coloured region is the only real one, is the only one which is not an abstraction. It should be observed that in taking a square as the representation of a cube on a plane, we only represent one face or the section between 2 faces. The squares, as drawn by a plane being, are not the cubes themselves, but represent the faces or the sections of a cube. Thus, in the plane being's diagram, figure 101, a cube of 27 cubes, null represents a cube, but is really in the normal position the orange square of a null cube, and may be called null orange square. A plane being would save himself confusion if he named his representative squares not by using the names of the cubes simply, but by adding to the names of the cubes a word to show what part of a cube his representative square was. Thus a cube null standing against his plane touches it by null orange face. Passing through his plane, it has in the plane a square as trace, which is null white section, if we use the phrase white section to mean a section drawn perpendicular to the white line. In the same way, the cubes which we take as representative of the tesseract are not the tesseract itself, but definite faces or sections of it. In the preceding figures we should say then, not null, but null tesseract ochre cube, because the cube we actually have is the one determined by the 3 axes, white, red, yellow. There is another way in which we can regard the colour nomenclature of the boundaries of a tesseract. Consider a null point to move, tracing out a white line 1 inch in length, and terminating in a null point. See figure 103, or in the coloured plate. Then consider this white line with its terminal points, itself to move in a 2nd dimension. Each of the points traces out a line, the line itself traces out an area, and gives 2 lines as well, its initial and its final position. Thus, if we call a region any element of the figure, such as a point or a line, etc., every region in moving traces out a new kind of region, a higher region, and gives 2 regions of its own kind, an initial and a final position. The higher region means a region with another dimension in it. Now the square can move and generate a cube. The square, light yellow, moves and traces out the mass of the cube. Letting the addition of red denote the region made by the motion in the upward direction, we get an ochre solid. The light yellow face in its initial and terminal positions gives the two square boundaries of the cube, above and below. Then each of the four lines of the light yellow square, white, yellow, and the white yellow opposite them, trace out a bounding square. So there are in all 6 bounding squares 4 of these squares being designated in colour by adding red to the colour of the generating lines. Finally, each point moving in the up direction gives rise to a line coloured null plus red, or red, and then there are the initial and terminal positions of the points, giving 8 points. The number of the lines is evidently 12, for the 4 lines of this light yellow square give 4 lines in their initial, 4 lines in their final position, while the 4 points trace out 4 lines, that is, altogether 12 lines. Now the squares are, each of them, separate boundaries of the cube, while the lines belong, each of them, to 2 squares. Thus the red line is that which is common to the orange and pink squares. Now suppose that there is a direction, the 4th dimension, which is perpendicular alike to every one of the space dimensions already used. A dimension perpendicular, for instance, to up and to right hand, so that the pink square moving in this direction traces out a cube. A dimension, moreover, perpendicular to the up and away directions, so that the orange square moving in this direction also traces out a cube, and the light yellow square too, moving in this direction, traces out a cube. Under this supposition, the whole cube moving in the unknown dimension traces out something new, a new kind of volume, a higher volume. This higher volume is a 4-dimensional volume, and we designate it in colour by adding blue to the colour of that which by moving generates it. It is generated by the motion of the ochre solid, and hence it is of the colour we call light brown. Note, white, yellow, red, blue, mixed together. End note. It is represented by a number of sections, like 2 in figure 103. Now this light brown higher solid has for boundaries, first, the ochre cube in its initial position, second, the same cube in its final position, 1 and 3, figure 103. Each of the squares which bound the cube, moreover, by movement in this new direction, traces out a cube. So we have, from the front pink faces of the cube, third, a pink-blue or light purple cube, shown as a light purple face on cube 2 in figure 103, this cube standing for any number of intermediate sections. Fourth, a similar cube from the opposite pink face. Fifth, a cube traced out by the orange face. This is coloured brown, and is represented by the brown face of the section cube in figure 103. Sixth, a corresponding brown cube on the right hand. Seventh, a cube starting from the light yellow square below. The unknown dimension is at right angles to this also. This cube is coloured light yellow and blue, or light green. And finally, eighth, a corresponding cube from the upper light yellow face, shown as the light green square at the top of the section cube. The tesseract has thus 8 cubic boundaries. These completely enclose it, so that it would be invisible to a 4-dimensional being. Now, as to the other boundaries, just as the cube has squares, lines, points as boundaries, so the tesseract has cubes, squares, lines, points as boundaries. The number of squares is found thus. Round the cube are 6 squares. These will give 6 squares in their initial and 6 in their final positions. Then each of the 12 lines of the cube trace out a square in the motion in the 4th dimension. Hence there will be altogether 12 plus 12 equals 24 squares. If we look at any one of these squares, we see that it is the meeting surface of two of the cubic sides. Thus the red line, by its movement in the fourth dimension, traces out a purple square. This is common to two cubes, one of which is traced out by the pink square moving in the fourth dimension, and the other is traced out by the orange square moving in the same way. To take another square, the light yellow one, this is common to the ochre cube and the light green cube. The ochre cube comes from the light yellow square by moving it in the up direction. The light green cube is made from the light yellow square by moving it in the fourth dimension. The number of lines is 32, for the 12 lines of the cube give 12 lines of the tesseract in their initial position and 12 in their final position, making 24, while each of the 8 points traces out a line, thus forming 32 lines altogether. The lines are each of them common to 3 cubes, or to 3 square faces. Take for instance the red line. This is common to the orange face, the pink face, and that face which is formed by moving the red line in the fourth dimension. Reader's note: by an apparent typographical error, this is given as sixth dimension in the text. End reader's note. Namely, the purple face. It is also common to the ochre cube, the pale purple cube, and the brown cube. The points are common to 6 square faces and to 4 cubes. Thus, the null point from which we start is common to the 3 square faces, pink, light yellow, orange, and to the 3 square faces made by moving the 3 lines, white, yellow, red, in the fourth dimension, namely the light blue, the light green, the purple faces, that is, to 6 faces in all. The 4 cubes which meet in it are the ochre cube, the light purple cube, the brown cube, and the light green cube. A complete view of the tesseract in its various space presentations is given in the following figures, or catalogue cubes, figures 103 to 106. The first cube in each figure represents the view of a tesseract, coloured as described, as it begins to pass transverse to our space. The intermediate figure represents a sectional view, when it is partly through, and the final figure represents the far end, as it is just passing out. These figures will be explained in detail in the next chapter. We have thus obtained a nomenclature for each of the regions of a tesseract. We can speak of any one of the 8 bounding cubes, the 20 square faces, the 32 lines, the 16 points. End of section 21. Section 22 of The Fourth Dimension by Charles Howard Hinton. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 13. Remarks on the Figures, Part 1. An inspection of above figures will give an answer to many questions about the tesseract. If we have a tesseract 1 inch each way, then it can be represented as a cube having white, yellow, red axes, and from this cube as a beginning, a volume extending into the fourth dimension. Now suppose the tesseract to pass transverse to our space. The cube of the red, yellow, white axes disappears at once. It is indefinitely thin in the fourth dimension. Its place is occupied by those parts of the tesseract which lie further away from our space in the fourth dimension. Each one of these sections will last only for 1 moment, but the whole of them will take up some appreciable time in passing. If we take the rate of 1 inch a minute, the sections will take the whole of the minute in their passage across our space. They will take the whole of the minute, except the moment which the beginning cube and the end cube occupy in their crossing our space. In each one of the cubes, the section cubes, we can draw lines in all directions except in the direction occupied by the blue line, the fourth dimension. Lines in that direction are represented by the transition from one section cube to another. Thus, to give ourselves an adequate representation of the tesseract, we ought to have a limitless number of section cubes intermediate between the first bounding cube, the ochre cube, and the last bounding cube, the other ochre cube. Practically, 3 intermediate sectional cubes will be found sufficient for most purposes. We will take then a series of 5 figures, 2 terminal cubes and 3 intermediate sections, and show how the different regions appear in our space when we take each set of 3 out of the 4 axes of the tesseract as lying in our space. In figure 107, initial letters are used for the colours. A reference to figure 103 will show the complete nomenclature, which is merely indicated here. In this figure, the tesseract is shown in 5 stages distant from our space. First, 0, second, 1/4 of an inch, third, 2/4 of an inch, fourth, 3/4 of an inch, fifth, 1 inch, which are called B0, B1, B2, B3, B4, because they are sections taken at distances 0, 1, 2, 3, 4 1/4 inches along the blue line. All the regions can be named from the first cube, the B0 cube, as before, simply by remembering that transference along the B axis gives the addition of blue to the colour of the region in the ochre, the B0 cube. In the final cube, B4, the colouring of the original B0 cube is repeated. Thus, the red line moved along the blue axis gives a red and blue, or purple, square. This purple square appears as the 3 purple lines in the sections B1, B2, B3, taken at 1/4, 2/4, 3/4 of an inch in the 4th dimension. If the tesseract moves transverse to our space, we have then in this particular region, first of all a red line, which lasts for a moment, secondly a purple line, which takes its place. This purple line lasts for a minute, that is, all of a minute except the moment taken by the crossing our space of the initial and final red line. The purple line having lasted for this period is succeeded by a red line, which lasts for a moment. Then this goes, and the tesseract has passed across our space. The final red line we call red BL, because it is separated from the initial red line by a distance along the axis for which we use the colour blue. Thus a line that lasts represents an area duration, is, in this mode of presentation, equivalent to a dimension of space. In the same way, the white line, during the crossing our space by the tesseract, is succeeded by a light blue line, which lasts for the inside of a minute. And as the tesseract leaves our space, having crossed it, the white BL line appears as the final termination. Take now the pink face. Moved in the blue direction, it traces out a light purple cube. This light purple cube is shown in sections in B1, B2, B3, and the farther face of this cube in the blue direction is shown in B4, a pink face, called pink B, because it is distant from the pink face we began with in the blue direction. Thus the cube which we colour light purple appears as a lasting square. The square face itself, the pink face, vanishes instantly the tesseract begins to move, but the light purple cube appears as a lasting square. Here also duration is the equivalent of a dimension of space. A lasting square is a cube. It is useful to connect these diagrams with the views given in the coloured plate. Take again the orange face, that determined by the red and yellow axes. From it goes a brown cube in the blue direction, for red and yellow and blue are supposed to make brown. This brown cube is shown in 3 sections in the faces B1, B2, B3. In B4 is the opposite orange face of the brown cube, the face called orange B, for it is distant in the blue direction from the orange face. As the tesseract passes transverse to our space, we have then in this region an instantly vanishing orange square, followed by a lasting brown square, and finally an orange face, which vanishes instantly. Now, as any three axes will be in our space, let us send the white axis out into the unknown, the fourth dimension, and take the blue axis into our known space dimension. Since the white and blue axes are perpendicular to each other, if the white axis goes out into the fourth dimension in the positive sense, the blue axis will come into the direction the white axis occupied in the negative sense. Hence, not to complicate matters by having to think of two senses in the unknown direction, let us send the white line into the positive sense of the fourth dimension, and take the blue one as running in the negative sense of that direction which the white line has left. Let the blue line, that is, run to the left. We have now the row of figures in figure 108. The dotted cube shows where we had a cube when the white line ran in our space. Now it has turned out of our space, and another solid boundary, another cubic face of the tesseract, comes into our space. This cube has red and yellow axes as before, but now instead of a white axis running to the right, there is a blue axis running to the left. Here we can distinguish the regions by colours in a perfectly systematic way. The red line traces out a purple square in the transference along the blue axis by which this cube is generated from the orange face. This purple square, made by the motion of the red line, is the same purple face that we saw before as a series of lines in the sections B1, B2, B3. Here, since both red and blue axes are in our space, we have no need of duration to represent the area they determine. In the motion of the tesseract across space, this purple face would instantly disappear. From the orange face, which is common to the initial cubes in figure 107 and figure 108, there goes in the blue direction a cube coloured brown. This brown cube is now all in our space, because each of its three axes run in space directions, up, away, to the left. It is the same brown cube which appeared as the successive faces on the sections B1, B2, B3. Having all its three axes in our space, it is given in extension. No part of it needs to be represented as a succession. The tesseract is now in a new position with regard to our space, and when it moves across our space, the brown cube instantly disappears. In order to exhibit the other regions of the tesseract, we must remember that now the white line runs in the unknown dimension. Where shall we put the sections at distances along the line? Any arbitrary position in our space will do. There is no way by which we can represent their real position. However, as the brown cube comes off from the orange face to the left, let us put these successive sections to the left. We can call them WH0, WH1, WH2, WH3, WH4, because they are sections along the white axis, which now runs in the unknown dimension. Running from the purple square in the white direction, we find the light purple cube. This is represented in the sections WH1, WH2, WH3, WH4, figure 108. It is the same cube that is represented in the sections B1, B2, B3. In figure 107, the red and white axes are in our space, the blue out of it. In the other case, the red and blue are in our space, the white out of it. It is evident that the face pink Y, opposite the pink face in figure 107, makes a cube shown in squares in B1, B2, B3, B4, on the opposite side to the L purple squares. Also, the light yellow face at the base of the cube B0 makes a light green cube, shown as a series of base squares. The same light green cube can be found in figure 107. The base square in WH0 is a green square, for it is enclosed by blue and yellow axes. From it goes a cube in the white direction. This is then a light green cube, and the same as the one just mentioned as existing in the sections B0, B1, B2, B3, B4. The case is, however, a little different with the brown cube. This cube we have altogether in space in the section WH0, figure 108, while it exists as a series of squares, the left-hand ones, in the sections B0, B1, B2, B3, B4. The brown cube exists as a solid in our space, as shown in figure 108. In the mode of representation of the tesseract exhibited in figure 107, the same brown cube appears as a succession of squares. That is, as the tesseract moves across space, the brown cube would actually be to us a square. It would be merely the lasting boundary of another solid. It would have no thickness at all, only extension in 2 dimensions, and its duration would show its solidity in 3 dimensions. It is obvious that if there is a 4-dimensional space, matter in 3 dimensions only is a mere abstraction. All material objects must then have a slight 4-dimensional thickness. In this case, the above statement will undergo modification. The material cube which is used as the model of the boundary of a tesseract will have a slight thickness in the 4th dimension, and when the cube is presented to us in another aspect, it would not be a mere surface. But it is most convenient to regard the cubes we use as having no extension at all in the 4th dimension. This consideration serves to bring out a point alluded to before, that if there is a 4th dimension, our conception of a solid is the conception of a mere abstraction, and our talking about real 3-dimensional objects would seem to a 4-dimensional being as incorrect as a 2-dimensional being's telling about real squares, real triangles, etc. would seem to us. The consideration of the 2 views of the brown cube shows that any section of a cube can be looked at by a presentation of the cube in a different position in 4-dimensional space. The brown faces in B1, B2, B3 are the very same brown sections that would be obtained by cutting the brown cube, WH0, across at the right distances along the blue line, as shown in figure 108. But as these sections are placed in the brown cube, WH0, they come behind one another in the blue direction. Now, in the sections WH1, WH2, WH3, we are looking at these sections from the white direction. The blue direction does not exist in these figures, so we see them in a direction at right angles to that in which they occur behind one another in WH0. There are intermediate views, which would come in the rotation of a tesseract. These brown squares can be looked at from directions intermediate between the white and blue axes. It must be remembered that the 4th dimension is perpendicular equally to all 3 space axes. Hence we must take the combinations of the blue axis with each 2 of our 3 axes, white, red, yellow, in turn. In figure 109 we take red, white and blue axes in space, sending yellow into the 4th dimension. If it goes into the positive sense of the 4th dimension, the blue line will come in the opposite direction to that in which the yellow line ran before. Hence the cube determined by the white, red, blue axes will start from the pink plane and run towards us. The dotted cube shows where the ochre cube was. When it is turned out of space, the cube coming towards from its front face is the one which comes into our space in this turning. Since the yellow line now runs in the unknown dimension, we call the sections y0, y1, y2, y3, y4, as they are made at distances 0, 1, 2, 3, 4 quarter inches along the yellow line. We suppose these cubes arranged in a line coming towards us. Not that that is any more natural than any other arbitrary series of positions, but it agrees with the plan previously adopted. The interior of the first cube, y0, is that derived from pink by adding blue, or, as we call it, light purple. The faces of the cube are light blue, purple, pink. As drawn, we can only see the face nearest to us, which is not the one from which the cube starts, but the face on the opposite side has the same colour name as the face towards us. The successive sections of the series y0, y1, y2, etc. can be considered as derived from sections of the B0 cube made at distances along the yellow axis. What is distant a quarter inch from the pink face in the yellow direction? This question is answered by taking a section from a point a quarter inch along the yellow axis in the cube B0, figure 107. It is an ochre section with lines orange and light yellow. This section will therefore take the place of the pink face in y1 when we go on in the yellow direction. Thus the first section, y1, will begin from an ochre face with light yellow and orange lines. The colour of the axis which lies in space towards us is blue, hence the regions of this section cube are determined in nomenclature. They will be found in full in figure 105. There remains only one figure to be drawn, and that is the one in which the red axis is replaced by the blue. Here, as before, if the red axis goes out into the positive sense of the fourth dimension, the blue line must come into our space in the negative sense of the direction which the red line has left. Accordingly, the first cube will come in beneath the position of our ochre cube, the one we have been in the habit of starting with. Reader's note, figure 110, end reader's note. To show these figures, we must suppose the ochre cube to be on a movable stand. When the red line swings out into the unknown dimension, and the blue line comes in downwards, a cube appears below the place occupied by the ochre cube. The dotted cube shows where the ochre cube was. That cube has gone, and a different cube runs downwards from its base. This cube has white, yellow, and blue axes. Its top is a light yellow square, and hence its interior is light yellow plus blue, or light green. Its front face is formed by the white line moving along the blue axis, and is therefore light blue. The left-hand side is formed by the yellow line moving along the blue axis, and therefore green. As the red line now runs in the fourth dimension, the successive sections can be called R0, R1, R2, R3, R4, these letters indicating that at distances 0, a quarter, 2 quarters, 3 quarters, 1 inch along the red axis, we take all of the tesseract that can be found in a three-dimensional space. This three-dimensional space extending not at all in the fourth dimension, but up and down, right and left, far and near. We can see what should replace the light yellow face of R0 when the section R1 comes in by looking at the cube B0, figure 107. What is distant in it 1/4 of an inch from the light yellow face in the red direction? It is an ochre section with orange and pink lines and red points. See also figure 103. This square then forms the top square of R1. Now we can determine the nomenclature of all the regions of R1 by considering what would be formed by the motion of this square along a blue axis. But we can adopt another plan. Let us take a horizontal section of R0, and finding that section in the figures of figure 107 or figure 103, from them determine what will replace it, going on in the red direction. A section of the R0 cube has green, light blue sides and blue points. Now this square occurs on the base of each of the section figures B1, B2, etc. In them we see that 1/4 of an inch in the red direction from it lies a section with brown and light purple lines and purple corners, the interior being of light brown. Hence this is the nomenclature of the section which in R1 replaces the section of R0 made from a point along the blue axis. Hence the colouring as given can be derived. We have thus obtained a perfectly named group of tesseracts we can take a group of 81 of them, 3 times 3 times 3 times 3, in 4 dimensions, and each tesseract will have its name null, red, white, yellow, blue, etc. And whatever cubic view we take of them, we can say exactly what sides of the tesseracts we are handling, and how they touch each other. Footnote: at this point the reader will find it advantageous, if he has the models, to go through the manipulations described in the appendix. End footnote. Thus, for instance, if we have the 16 tesseracts shown below, we can ask, how does null touch blue? In the arrangement given in figure 111, we have the axes white, red, yellow in space, blue running in the 4th dimension. Hence we have the ochre cubes as bases. Imagine now the tesseractic group to pass transverse to our space. We have, first of all, null ochre cube, white ochre cube, etc. These instantly vanish, and we get the section shown in the middle cube in figure 103. And finally, just when the tesseract block has moved 1 inch transverse to our space, we have null ochre cube, and then immediately afterwards the ochre cube of blue comes in. Hence the tesseract null touches the tesseract blue by its ochre cube, which is in contact, each and every point of it, with the ochre cube of blue. How does null touch white, we may ask? Looking at the beginning A, figure 111, where we have the ochre cubes, we see that null ochre touches white ochre by an orange face. Now let us generate the null and white tesseracts by a motion in the blue direction of each of these cubes. Each of them generates the corresponding tesseract, and the plane of contact of the cubes generates the cube by which the tesseracts are in contact. Now an orange plane carried along a blue axis generates a brown cube, hence null touches white by a brown cube. If we ask again how red touches light blue tesseract, let us rearrange our group, figure 112, or rather turn it about so that we have a different space view of it. Let the red axis and the white axis run up and right, and let the blue axis come in space towards us. Then the yellow axis runs in the 4th dimension. We have then 2 blocks in which the bounding cubes of the tesseracts are given, differently arranged with regard to us. The arrangement is really the same, but it appears different to us. Starting from the plane of the red and white axes, we have the 4 squares of the null, white, red, pink tesseracts, as shown in A, on the red, white plane unaltered, only from them now comes out towards us the blue axis. Hence we have null, white, red, pink tesseracts in contact with our space by their cubes which have the red, white, blue axis in them, that is, by the light purple cubes. Following on these 4 tesseracts, we have that which comes next to them in the blue direction, that is, the 4 blue, light blue, purple, light purple. These are likewise in contact with our space by their light purple cubes, so we see a block, as named in the figure, of which each cube is the one determined by the red, white, blue axes. The yellow line now runs out of space. Accordingly, 1 inch on in the 4th dimension, we come to the tesseracts which follow on the 8 named in C, figure 112, in the yellow direction. These are shown in CY1, figure 112. Between figure C and CY1 is that 4th dimensional mass which is formed by moving each of the cubes in C 1 inch in the 4th dimension, that is, along a yellow axis, for the yellow axis now runs in the 4th dimension. In the block C we observe that red, light purple cube, touches light blue, light purple cube, by a point. Now these 2 cubes moving together remain in contact during the period in which they trace out the tesseracts red and light blue. This motion is along the yellow axis. Consequently, red and light blue touch by a yellow line. End of section 22. Section 23 of The Fourth Dimension by Charles Howard Hinton. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 13. Remarks on the Figures, Part 2. We have seen that the pink face, moved in a yellow direction, traces out a cube. Moved in the blue direction, it also traces out a cube. Let us ask what the pink face will trace out if it is moved in a direction within the tesseract lying equally between the yellow and blue directions. What section of the tesseract will it make? We will first consider the red line alone. Let us take a cube with the red line in it and the yellow and blue axes. The cube with the yellow, red, blue axes is shown in figure 113. If the red line is moved equally in the yellow and in the blue direction by 4 equal motions of 1/4 of an inch each, it takes the positions 1, 1, 2, 2, 3, 3 and ends as a red line. Now the whole of this red, yellow, blue or brown cube appears as a series of faces on the successive sections of the tesseract, starting from the ochre cube and letting the blue axis run in the fourth dimension. Hence, the plane traced out by the red line appears as a series of lines in the successive sections in our ordinary way of representing the tesseract. These lines are in different places in each successive section. Thus, drawing our initial cube and the successive sections, calling them B0, B1, B2, B3, B4, figure 114, we have the red line subject to this movement appearing in the positions indicated. We will now investigate what positions in the tesseract another line in the pink face assumes when it is moved in a similar manner. Take a section of the original cube containing a vertical line, 4, in the pink plane, figure 115. We have in the section the yellow direction, but not the blue. From this section a cube goes off in the fourth dimension, which is formed by moving each point of the section in the blue direction. Drawing this cube, we have figure 116. Now this cube occurs as a series of sections in our original representation of the tesseract. Taking 4 steps as before, this cube appears as the sections drawn in B0, B1, B2, B3, B4, figure 117, and if the line 4 is subjected to a movement equal in the blue and yellow directions, it will occupy the positions designated by 4, 41, 42, 43, 44. Hence, reasoning in a similar manner about every line, it is evident that, moved equally in the blue and yellow directions, the pink plane will trace out a space which is shown by the series of section planes represented in the diagram. Thus the space traced out by the pink face, if it is moved equally in the yellow and blue directions, is represented by the set of planes delineated in figure 118. Pink face, or 0, then 1, 2, 3, and finally pink face, or 4. This solid is a diagonal solid of the tesseract, running from a pink face to a pink face. Its length is the length of the diagonal of a square. Its side is a square. Let us now consider the unlimited space which springs from the pink face extended. This space, if it goes off in the yellow direction, gives us in it the ochre cube of the tesseract. Thus, if we have the pink face given, and a point in the ochre cube, we have determined this particular space. Similarly, going off from the pink face in the blue direction is another space, which gives us the light purple cube of the tesseract in it. And any point being taken in the light purple cube, this space going off from the pink face is fixed. The space we are speaking of can be conceived as swinging round the pink face, and in each of its positions it cuts out a solid figure from the tesseract, one of which we have seen represented in figure 118. Each of these solid figures is given by one position of the swinging space and by one only. Hence, in each of them, if one point is taken, the particular one of the slanting spaces is fixed. Thus we see that given a plane and a point out of it, a space is determined. Now 2 points determine a line. Again, think of a line and a point outside it. Imagine a plane rotating round the line. At some time in its rotation, it passes through the point. Thus a line and a point, or 3 points, determine a plane. And finally, 4 points determine a space. We have seen that a plane and a point determine a space, and that 3 points determine a plane, so 4 points will determine a space. These 4 points may be any points, and we can take, for instance, the 4 points at the extremities of the red, white, yellow, blue axes in the tesseract. These will determine a space slanting with regard to the section spaces we have been previously considering. This space will cut the tesseract in a certain figure. One of the simplest sections of a cube by a plane is that in which the plane passes through the extremities of the 3 edges which meet in a point. We see at once that this plane would cut the cube in a triangle, but we will go through the process by which a plane being would most conveniently treat the problem of the determination of this shape, in order that we may apply the method to the determination of the figure in which a space cuts a tesseract when it passes through the 4 points at unit distance from a corner. We know that 2 points determine a line, 3 points determine a plane, and given any 2 points in a plane, the line between them lies wholly in the plane. Let now the plane being study the section made by a plane passing through the null R, null WH and null Y points, figure 119. Looking at the orange square, which, as usual, we suppose to be initially in his plane, he sees that the line from null R to null Y, which is a line in the section plane, the plane namely through the 3 extremities of the edges meeting in null, cuts the orange face in an orange line with null points. This, then, is one of the boundaries of the section figure. Let now the cube be so turned that the pink face comes in his plane. The points null R and null WH are now visible. The line between them is pink with null points, and since this line is common to the surface of the cube and the cutting plane, it is a boundary of the figure in which the plane cuts the cube. Again, suppose the cube turned so that the light yellow face is in contact with the plane being's plane. He sees 2 points, the null WH and the null Y. The line between these lies in the cutting plane. Hence, since the 3 cutting lines meet and enclose a portion of the cube between them, he has determined the figure he sought. It is a triangle with orange, pink and light yellow sides, all equal and enclosing an ochre area. Let us now determine in what figure the space determined by the 4 points null R, null Y, null WH, null B cuts the tesseract. We can see 3 of these points in the primary position of the tesseract resting against our solid sheet by the ochre cube. These 3 points determine a plane which lies in the space we are considering, and this plane cuts the ochre cube in a triangle, the interior of which is ochre. Note, figure 119 will serve for this view, end note, with pink, light yellow and orange sides, and null points. Going in the 4th direction, in one sense from this plane we pass into the tesseract, in the other sense we pass away from it. The whole area inside the triangle is common to the cutting plane we see, and a boundary of the tesseract. Hence we conclude that the triangle drawn is common to the tesseract and the cutting space. Now let the ochre cube turn out and the brown cube come in. The dotted lines show the position the ochre cube has left, figure 120. Here we see 3 out of the 4 points through which the cutting plane passes, null R, null Y and null B. The plane they determine lies in the cutting space, and this plane cuts out of the brown cube a triangle with orange, purple and green sides, and null points. The orange line of this figure is the same as the orange line in the last figure. Now let the light purple cube swing into our space towards us, figure 121. The cutting space, which passes through the 4 points, null R, Y, WH, B, passes through the null R, WH, B, and therefore the plane these determine lies in the cutting space. This triangle lies before us. It has a light purple interior and pink, light blue and purple edges with null points. This, since it is all of the plane that is common to it and this bounding of the tesseract, gives us one of the bounding faces of our sectional figure. The pink line in it is the same as the pink line we found in the first figure, that of the ochre cube. Finally, let the tesseract swing about the light yellow plane, so that the light green cube comes into our space. It will point downwards. The 3 points, NY, NWH, NB, are in the cutting space, and the triangle they determine is common to the tesseract and the cutting space. Hence, this boundary is a triangle having a light yellow line, which is the same as the light yellow line of the first figure, a light blue line, and a green line. Reader's note, figure 122, end reader's note. We have now traced the cutting space between every set of 3 that can be made out of the 4 points in which it cuts the tesseract, and have got 4 faces which all join onto each other by lines. The triangles are shown in figure 123, as they join on to the triangle in the ochre cube, but they join on each to the other in an exactly similar manner. Their edges are all identical, 2 and 2. They form a closed figure, a tetrahedron, enclosing a light brown portion, which is the portion of the cutting space which lies inside the tesseract. We cannot expect to see this light brown portion any more than a plane being could expect to see the inside of a cube if an angle of it were pushed through his plane. All he can do is to come upon the boundaries of it in a different way to that in which he would if it passed straight through his plane. Thus, in this solid section, the whole interior lies perfectly open in the 4th dimension. Go round it as we may, we are simply looking at the boundaries of the tesseract which penetrates through our solid sheet. If the tesseract were not to pass across so far, the triangle would be smaller. If it were to pass farther, we should have a different figure, the outlines of which can be determined in a similar manner. The preceding method is open to the objection that it depends rather on our inferring what must be than our seeing what is. Let us therefore consider our sectional space as consisting of a number of planes, each very close to the last, and observe what is to be found in each plane. The corresponding method in the case of 2 dimensions is as follows. The plane being can see that line of the sectional plane through null y, null w, null r, which lies in the orange plane. Let him now suppose the cube and the section plane to pass halfway through his plane. Replacing the red and yellow axes are lines parallel to them, sections of the pink and light yellow faces. Where will the section plane cut these parallels to the red and yellow axes? Let him suppose the cube in the position of the drawing figure 124 turned so that the pink face lies against his plane. He can see the line from the null R point to the null WH point, and can see, note, compare figure 119, end note, that it cuts AB, a parallel to his red axis, drawn at a point halfway along the white line, in a point B, halfway up. I shall speak of the axis as having the length of an edge of the cube. Similarly, by letting the cube turn so that the light yellow square swings against his plane, he can see, note, compare figure 119, end note, that a parallel to his yellow axis, drawn from a point halfway along the white axis, is cut at half its length by the trace of the section plane in the light yellow face. Hence, when the cube had passed halfway through, he would have, instead of the orange line with null points, which he had at first, an ochre line of half its length, with pink and light yellow points. Thus, as the cube passed slowly through his plane, he would have a succession of lines gradually diminishing in length and forming an equilateral triangle. The whole interior would be ochre, the line from which it started would be orange. The succession of points at the ends of the succeeding lines would form pink and light yellow lines, and the final point would be null. Thus, looking at the successive lines in the section plane as it and the cube passed across his plane, he would determine the figure cut out bit by bit. Coming now to the section of the tesseract, let us imagine that the tesseract and its cutting space pass slowly across our space. We can examine portions of it and their relation to portions of the cutting space. Take the section space which passes through the 4 points null R, WH, Y, B. We can see in the ochre cube, figure 119, the plane belonging to this section space, which passes through the 3 extremities of the red, white, yellow axes. Now let the tesseract pass halfway through our space. Instead of our original axes, we have parallels to them, purple, light blue, and green, each of the same length as the first axes, for the section of the tesseract is of exactly the same shape as its ochre cube. But the sectional space seen at this stage of the transference would not cut the section of the tesseract in a plane disposed as at first. To see where the sectional space would cut these parallels to the original axes, let the tesseract swing so that, the orange face remaining stationary, the blue line comes in to the left. Here, figure 125, we have the null R, Y, B points, and of the sectional space all we see is the plane through these 3 points in it. In this figure we can draw the parallels to the red and yellow axes, and see that if they started at a point halfway along the blue axis, they would each be cut at a point so as to be half of their previous length. Swinging the tesseract into our space about the pink face of the ochre cube, we likewise find that the parallel to the white axis is cut at half its length by the sectional space. Hence, in a section made when the tesseract had passed half across our space, the parallels to the red, white, yellow axes, which are now in our space, are cut by the section space, each of them halfway along, and for this stage of the traversing motion we should have figure 126. The section made of this cube by the plane in which the sectional space cuts it is an equilateral triangle with purple, light blue, green points, and light purple, brown, light green lines. Thus the original ochre triangle, with null points and pink, orange, light yellow lines, would be succeeded by a triangle coloured in manner just described. This triangle would initially be only a very little smaller than the original triangle. It would gradually diminish until it ended in a point, a null point. Each of its edges would be of the same length. Thus, the successive sections of the successive planes into which we analyse the cutting space would be a tetrahedron of the description shown, figure 123, and the whole interior of the tetrahedron would be light brown. In figure 127, the tetrahedron is represented by means of its faces as 2 triangles which meet in the pink line, and 2 rear triangles which join onto them, the diagonal of the pink face being supposed to run vertically upward. We have now reached a natural termination. The reader may pursue the subject in further detail, but will find no essential novelty. I conclude with an indication as to the manner in which figures previously given may be used in determining sections by the method developed above. Applying this method to the tesseract, as represented in Chapter 9, sections made by a space cutting the axes equidistantly at any distance can be drawn, and also the sections of tesseracts arranged in a block. If we draw a plane cutting all 4 axes at a point 6 units distance from null, we have a slanting space. This space cuts the red, white, yellow axes in the points L, M, N, figure 128, and so in the region of our space before we go off into the 4th dimension, we have the plane represented by LMN extended. This is what is common to the slanting space and our space. This plane cuts the ochre cube in the triangle EFG. Comparing this with figure 72, OH, we see that the hexagon there drawn is part of the triangle EFG. Let us now imagine the tesseract and the slanting space both together to pass transverse to our space, a distance of 1 unit. We have in 1H a section of the tesseract, whose axes are parallels to the previous axes. The slanting space cuts them at a distance of 5 units along each. Drawing the plane through these points in 1H, it will be found to cut the cubical section of the tesseract in the hexagonal figure drawn. In 2H, figure 72, the slanting space cuts the parallels to the axes at a distance of 4 along each, and the hexagonal figure is the section of this section of the tesseract by it. Finally, when 3H comes in, the slanting space cuts the axes at a distance of 3 along each, and the section is a triangle, of which the hexagon drawn is a truncated portion. After this, the tesseract, which extends only 3 units in each of the 4 dimensions, has completely passed transverse of our space, and there is no more of it to be cut. Hence, putting the plane sections together in the right relations, we have the section determined by the particular slanting space, namely an octahedron. End of section 23. Section 24 of The Fourth Dimension by Charles Howard Hinton. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 14. A recapitulation and extension of the physical argument. Part 1. Footnote. The contents of this chapter are taken from a paper read before the Philosophical Society of Washington. The mathematical portion of the paper has appeared in part in the Proceedings of the Royal Irish Academy under the title Cayley's Formulae of Orthogonal Transformation, November the 29th, 1903. End footnote. There are 2 directions of inquiry in which the research for the physical reality of a 4th dimension can be prosecuted. One is the investigation of the infinitely great, the other is the investigation of the infinitely small. By the measurement of the angles of vast triangles, whose sides are the distances between the stars, astronomers have sought to determine if there is any deviation from the values given by geometrical deduction. If the angles of a celestial triangle do not together equal 2 right angles, there would be an evidence for the physical reality of a 4th dimension. This conclusion deserves a word of explanation. If space is really 4-dimensional, certain conclusions follow which must be brought clearly into evidence if we are to frame the questions definitely which we put to nature. To account for our limitation, let us assume a solid material sheet against which we move. This sheet must stretch alongside every object in every direction in which it visibly moves. Every material body must slip or slide along this sheet, not deviating from contact with it in any motion which we can observe. The necessity for this assumption is clearly apparent if we consider the analogous case of a suppositionary plane world. If there were any creatures whose experiences were confined to a plane, we must account for their limitation. If they were free to move in every space direction, they would have a 3-dimensional motion. Hence, they must be physically limited, and the only way in which we can conceive such a limitation to exist is by means of a material surface against which they slide. The existence of this surface could only be known to them indirectly. It does not lie in any direction from them in which the kinds of motion they know of lead them. If it were perfectly smooth and always in contact with every material object, there would be no difference in their relations to it which would direct their attention to it. But if this surface were curved, if it were, say, in the form of a vast sphere, the triangles they drew would really be triangles of a sphere, and when these triangles are large enough, the angles diverge from the magnitudes they would have for the same lengths of sides if the surface were plane. Hence, by the measurement of triangles of very great magnitude, a plane being might detect a difference from the laws of a plane world in his physical world, and so be led to the conclusion that there was in reality another dimension to space, a third dimension, as well as the two which his ordinary experience made him familiar with. Now, astronomers have thought it worth while to examine the measurements of vast triangles drawn from one celestial body to another, with a view to determine if there is anything like a curvature in our space. That is to say, they have tried astronomical measurements to find out if the vast solid sheet against which, on the supposition of a fourth dimension, everything slides is curved or not. These results have been negative. The solid sheet, if it exists, is not curved, or, being curved, has not a sufficient curvature to cause any observable deviation from the theoretical value of the angles calculated. Hence the examination of the infinitely great leads to no decisive criterion. If it did, we should have to decide between the present theory and that of metageometry. Coming now to the prosecution of the inquiry in the direction of the infinitely small, we have to state the question thus. Our laws of movement are derived from the examination of bodies which move in three-dimensional space. All our conceptions are founded on the supposition of a space which is represented analytically by three independent axes and variations along them. That is, it is a space in which there are three independent movements. Any motion possible in it can be compounded out of these three movements, which we may call up, right, away. To examine the actions of the very small portions of matter with the view of ascertaining if there is any evidence in the phenomena for the supposition of a fourth dimension of space, we must commence by clearly defining what the laws of mechanics would be on the supposition of a fourth dimension. It is of no use asking if the phenomena of the smallest particles of matter are like we do not know what. We must have a definite conception of what the laws of motion would be on the supposition of the fourth dimension, and then inquire if the phenomena of the activity of the smaller particles of matter resemble the conceptions which we have elaborated. Now, the task of forming these conceptions is by no means one to be lightly dismissed. Movement in space has many features which differ entirely from movement on a plane, and when we set about to form the conception of motion in 4 dimensions, we find that there is at least as great a step as from the plane to 3-dimensional space. I do not say that the step is difficult, but I want to point out that it must be taken. When we have formed the conception of 4-dimensional motion, we can ask a rational question of nature. Before we have elaborated our conceptions, we are asking if an unknown is like an unknown, a futile inquiry. As a matter of fact, 4-dimensional movements are in every way simple and more easy to calculate than 3-dimensional movements, for 4-dimensional movements are simply 2 sets of plane movements put together. Without the formation of an experience of 4-dimensional bodies, their shapes and motions, the subject can be but formal, logically conclusive, not intuitively evident. It is to this logical apprehension that I must appeal. It is perfectly simple to form an experiential familiarity with the facts of 4-dimensional movement. The method is analogous to that which a plane being would have to adopt to form an experiential familiarity with 3-dimensional movements, and may be briefly summed up as the formation of a compound sense by means of which duration is regarded as equivalent to extension. Consider a being confined to a plane. A square enclosed by 4 lines will be to him a solid, the interior of which can only be examined by breaking through the lines. If such a square were to pass transverse to his plane, it would immediately disappear. It would vanish, going in no direction to which he could point. If now a cube be placed in contact with his plane, its surface of contact would appear like the square which we have just mentioned. But if it were to pass transverse to his plane, breaking through it, it would appear as a lasting square. The 3-dimensional matter will give a lasting appearance in circumstances under which 2-dimensional matter will at once disappear. Similarly, a 4-dimensional cube, or as we may call it, a tesseract, which is generated from a cube by a movement of every part of the cube in a 4th direction at right angles to each of the 3 visible directions in the cube, if it moved transverse to our space, would appear as a lasting cube. A cube of 3-dimensional matter, since it extends to no distance at all in the 4th dimension, would instantly disappear if subjected to a motion transverse to our space. It would disappear and be gone, without it being possible to point to any direction in which it had moved. All attempts to visualize a 4th dimension are futile. It must be connected with a time experience in 3 space. The most difficult notion for a plane being to acquire would be that of rotation about a line. Consider a plane being facing a square. If he were told that rotation about a line were possible, he would move his square this way and that. A square in a plane can rotate about a point, but to rotate about a line would seem to the plane being perfectly impossible. How could those parts of his square which were on one side of an edge come to the other side without the edge moving? He could understand their reflection in the edge. He could form an idea of the looking-glass image of his square lying on the opposite side of the line of an edge, but by no motion that he knows of can he make the actual square assume that position. The result of the rotation would be like reflection in the edge, but it would be a physical impossibility to produce it in the plane. The demonstration of rotation about a line must be to him purely formal. If he conceived the notion of a cube stretching out in an unknown direction away from his plane, then he can see the base of it, his square in the plane, rotating round a point. He can likewise apprehend that every parallel section taken at successive intervals in the unknown direction rotates in like manner round a point. Thus he would come to conclude that the whole body rotates round a line, the line consisting of the succession of points round which the plane sections rotate. Thus, given 3 axes, x, y, z, if x rotates to take the place of y, and y turns so as to point to negative x, then the 3rd axis remaining unaffected by this turning is the axis about which the rotation takes place. This then would have to be his criterion of the axis of a rotation, that which remains unchanged when a rotation of every plane section of a body takes place. There is another way in which a plane being can think about 3-dimensional movements, and as it affords the type by which we can most conveniently think about 4-dimensional movements, it will be no loss of time to consider it in detail. We can represent the plane being and his object by figures cut out of paper, which slip on a smooth surface. The thickness of these bodies must be taken as so minute that their extension in the 3rd dimension escapes the observation of the plane being, and he thinks about them as if they were mathematical plane figures in a plane, instead of being material bodies capable of moving on a plane surface. Reader's note. Figure 1. End reader's note. Let AX, AY be 2 axes and ABCD a square. As far as movements in the plane are concerned, the square can rotate about a point A, for example. It cannot rotate about a side, such as AC. But if the plane being is aware of the existence of a 3rd dimension, he can study the movements possible in the ample space, taking his figure portion by portion. His plane can only hold two axes, but since it can hold two, he is able to represent a turning into the third dimension if he neglect one of his axes and represent the third axis as lying in his plane. He can make a drawing in his plane of what stands up perpendicularly from his plane. Let AZ be the axis which stands perpendicular to his plane at A. He can draw in his plane two lines to represent the two axes, AX and AZ. Let figure 2 be this drawing. Here the Z-axis has taken the place of the Y-axis, and the plane of AX, AZ is represented in his plane. In this figure all that exists of the square ABCD will be the line AB. The square extends from this line in the Y direction, but more of that direction is represented in figure 2. The plane being can study the turning of the line AB in this diagram. It is simply a case of plane turning around the point A. The line AB occupies intermediate portions like AB1, and after half a revolution will lie on AX produced through A. Now in the same way the plane being can take another point A' and another line A'B' in his square. He can make the drawing of the two directions at A', one along A'B', the other perpendicular to his plane. He will obtain a figure precisely similar to figure 2, and will see that as AB can turn around A, so A'C' around A. In this turning, AB and A'B' would not interfere with each other as they would if they moved in the plane around the separate points A and A'. Hence the plane being would conclude that a rotation round a line was possible. He could see his square as it began to make this turning. He could see it halfway round when it came to lie on the opposite side of the line AC, but in intermediate portions he could not see it, for it runs out of the plane. Coming now to the question of a four-dimensional body, let us conceive of it as a series of cubic sections, the first in our space, the rest at intervals stretching away from our space in the unknown direction. We must not think of a four-dimensional body as formed by moving a three-dimensional body in any direction which we can see. Refer for a moment to figure 3. The point A moving to the right traces out the line AC. The line AC moving away in a new direction traces out the square ACEG at the base of the cube. The square AEGC moving in a new direction will trace out the cube ACEGBDHF. The vertical direction of this last motion is not identical with any motion possible in the plane of the base of the cube. It is an entirely new direction, at right angles to every line that can be drawn in the base. To trace out a tesseract, the cube must move in a new direction, a direction at right angles to any and every line that can be drawn in the space of the cube. The cubic sections of the tesseract are related to the cube we see, as the square sections of the cube are related to the square of its base, which a plane being sees. Let us imagine the cube in our space, which is the base of a tesseract, to turn about one of its edges. The rotation will carry the whole body with it, and each of the cubic sections will rotate. The axis we see in our space will remain unchanged, and likewise the series of axes parallel to it, about which each of the parallel cubic sections rotates. The assemblage of all of these is a plane. Hence, in 4 dimensions, a body rotates about a plane. There is no such thing as rotation round an axis. We may regard the rotation from a different point of view. Consider 4 independent axes, each at right angles to all the others, drawn in a 4-dimensional body. Of these 4 axes, we can see any 3. The 4th extends normal to our space. Rotation is the turning of one axis into a second, and the second turning to take the place of the negative of the first. It involves 2 axes. Thus, in this rotation of a 4-dimensional body, 2 axes change and 2 remain at rest. Four-dimensional rotation is therefore a turning about a plane. As in the case of a plane being, the result of rotation about a line would appear as the production of a looking glass image of the original object on the other side of the line, so to us the result of a four-dimensional rotation would appear like the production of a looking glass image of a body on the other side of a plane. The plane would be the axis of the rotation, and the path of the body between its two appearances would be unimaginable in three-dimensional space. Let us now apply the method by which a plane being could examine the nature of rotation about a line in our examination of rotation about a plane. Figure 3 represents a cube in our space, the three axes x, y, z denoting its three dimensions. Let W represent the fourth dimension. Now, since in our space we can represent any three dimensions, we can, if we choose, make a representation of what is in the space determined by the three axes x, z, w. This is a three-dimensional space determined by two of the axes we have drawn, x and z, and in place of y, the fourth axis, w. We cannot, keeping x and z, have both y and w in our space. So we will let y go and draw w in its place. What will be our view of the cube? Evidently we shall have simply the square that is in the plane of xz, the square ACDB. The rest of the cube stretches in the y direction, and as we have none of the space so determined, we have only the face of the cube. This is represented in figure 4. Now suppose the whole cube to be turned from the x to the w direction. Conformably with our method, we will not take the whole of the cube into consideration at once, but will begin with the face ABCD. Let this face begin to turn. Figure 5 represents one of the positions it will occupy. The line AB remains on the Z axis. The rest of the face extends between the X and the W direction. Now, since we can take any three axes, let us look at what lies in the space of ZYW and examine the turning there. We must now let the Z axis disappear and let the W axis run in the direction in which the Z ran. Making this representation, what do we see of the cube? Obviously, we see only the lower face. The rest of the cube lies in the space of XYZ. In the space of XYZ, we have merely the base of the cube lying in the plane of XY, as shown in figure 6. Now let the X to W turning take place. The square ACEG will turn about the line AE. This edge will remain along the Y axis and will be stationary, however far the square turns. Reader's note, figure 7, end reader's note. Thus, if the cube be turned by an X to W turning, both the edge AB and the edge AC remain stationary. Hence the whole face ABEF in the YZ plane remains fixed. The turning has taken place about the face ABEF. Suppose this turning to continue till AC runs to the left from A. The cube will occupy the position shown in figure 8. This is the looking glass image of the cube in figure 3. By no rotation in three-dimensional space can the cube be brought from the position in figure 3 to that shown in figure 8. We can think of this turning as a turning of the face ABCD about AB, and a turning of each section parallel to ABCD round the vertical line in which it intersects the face ABEF, the space in which the turning takes place being a different one from that in which the cube lies. One of the conditions, then, of our inquiry in the direction of the infinitely small is that we form the conception of a rotation about a plane. The production of a body in a state in which it presents the appearance of a looking glass image of its former state is the criterion for a four-dimensional rotation. There is some evidence for the occurrence of such transformations of bodies in the change of bodies from those which produce a right-handed polarization of light to those which produce a left-handed polarization, but this is not a point to which any very great importance can be attached. Still, in this connection, let me quote a remark from Professor John G. McKendrick's address on physiology before the British Association at Glasgow. Discussing the possibility of the hereditary production of characteristics through the material structure of the ovum, he estimates that in it there exist 12,000 million biophores, or ultimate particles of living matter, a sufficient number to account for hereditary transmission, and observes, "Thus it is conceivable that vital activities may also be determined by the kind of motion that takes place in the molecules of that which we speak of as living matter. It may be different in kind from some of the motions known to physicists, and it is conceivable that life may be the transmission to dead matter, the molecules of which already have a special kind of motion, of a form of motion sui generis." Now, in the realm of organic beings, symmetrical structures, those with a right and left symmetry, are everywhere in evidence. Granted that 4 dimensions exist, the simplest turning produces the image form, and by a folding over, structures could be produced, duplicated right and left, just as is the case of symmetry in a plane. Thus, one very general characteristic of the forms of organisms could be accounted for by the supposition that a 4-dimensional motion was involved in the process of life. But whether 4-dimensional motions correspond in other respects to the physiologist's demand for a special kind of motion or not, I do not know. Our business is with the evidence for their existence in physics. For this purpose it is necessary to examine into the significance of rotation round a plane in the case of extensible and of fluid matter. Let us dwell a moment longer on the rotation of a rigid body. Looking at the cube in figure 3, which turns about the face of ABFE, we see that any line in the face can take the place of the vertical and horizontal lines we have examined. Take the diagonal line AF and the section through it to GH. The portions of matter which were on one side of AF in this section in figure 3 are on the opposite side of it in figure 8. They have gone round the line AF. Thus the rotation round a face can be considered as a number of rotations of sections round parallel lines in it. The turning about 2 different lines is impossible in 3-dimensional space. To take another illustration, suppose A and B are 2 parallel lines in the XY plane, and let CD and EF be 2 rods crossing them. Now in the space of XYZ, if the rods turn round the lines A and B in the same direction, they will make 2 independent circles. When the end F is going down, the end C will be coming up. They will meet and conflict. Reader's note. Figure 9. End reader's note. But if we rotate the rods about the plane of AB by the Z to W rotation, these movements will not conflict. Suppose all the figure removed, with the exception of the plane XZ, and from this plane draw the axis of W, so that we are looking at the space of XZW. Here, figure 10, we cannot see the lines A and B. We see the points G and H, in which A and B intercept the x-axis. But we cannot see the lines themselves, for they run in the y direction, and that is not in our drawing. Now if the rods move with the Z to W rotation, they will turn in parallel planes, keeping their relative positions. The point D, for instance, will describe a circle. At one time it will be above the line A, at another time below it. Hence it rotates round A. Not only 2 rods, but any number of rods crossing the plane will move round it harmoniously. We can think of this rotation by supposing the rods standing up from one line to move round that line, and remembering that it is not inconsistent with this rotation for the rods standing up along another line also to move round it, the relative positions of all the rods being preserved. Now if the rods are thick together, they may represent a disk of matter, and we see that a disk of matter can rotate round a central plane. End of section 24. Section 25 of The Fourth Dimension by Charles Howard Hinton. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 14. A recapitulation and extension of the physical argument. Part 2. Rotation round a plane is exactly analogous to rotation round an axis in 3 dimensions. If we want a rod to turn round, the ends must be free. So, if we want a disk of matter to turn round its central plane by a 4-dimensional turning, all the contour must be free. The whole contour corresponds to the ends of the rod. Each point of the contour can be looked on as the extremity of an axis in the body, round each point of which there is a rotation of the matter in the disk. If the one end of a rod be clamped, we can twist the rod, but not turn it round. So if any part of the contour of a disk is clamped, we can impart a twist to the disk, but not turn it round its central plane. In the case of extensible materials, a long thin rod will twist round its axis, even when the axis is curved, as for instance in the case of a ring of India rubber. In an analogous manner, in 4 dimensions, we can have rotation round a curved plane, if I may use the expression. A sphere can be turned inside out in 4 dimensions. Let figure 11 represent a spherical surface, on each side of which a layer of matter exists. The thickness of the matter is represented by the rods CD and EF, extending equally without and within. Now take the section of the sphere by the YZ plane. We have a circle, figure 12. Now let the W-axis be drawn in place of the X-axis, so that we have the space of YZW represented. In this space, all that there will be seen of the sphere is the circle drawn. Here we see that there is no obstacle to prevent the rods turning round. If the matter is so elastic that it will give enough for the particles at E and C to be separated, as they are at F and D, they can rotate round to the position D and F, and a similar motion is possible for all other particles. There is no matter or obstacle to prevent them from moving out in the W direction, and then on round the circumference as an axis. Now, what will hold for one section will hold for all, as the 4th dimension is at right angles to all the sections which can be made of the sphere. We have supposed the matter of which the sphere is composed to be 3-dimensional. If the matter had a small thickness in the 4th dimension, there would be a slight thickness in figure 12 above the plane of the paper, a thickness equal to the thickness of the matter in the 4th dimension. The rods would have to be replaced by thin slabs. But this would make no difference as to the possibility of the rotation. This motion is discussed by Newcomb in the 1st volume of the American Journal of Mathematics. Let us now consider not a merely extensible body, but a liquid one. A mass of rotating liquid, a whirl, eddy, or vortex, has many remarkable properties. On first consideration, we should expect the rotating mass of liquid immediately to spread off and lose itself in the surrounding liquid. The water flies off a wheel whirled round, and we should expect the rotating liquid to be dispersed. But see the eddies in a river, strangely persistent. The rings that occur in puffs of smoke and last so long are whirls or vortices curved round so that their opposite ends join together. A cyclone will travel over great distances. Helmholtz was the first to investigate the properties of vortices. He studied them as they would occur in a perfect fluid, that is, one without friction of one moving portion or another. In such a medium, vortices would be indestructible. They would go on for ever, altering their shape, but consisting always of the same portion of the fluid. But a straight vortex could not exist surrounded entirely by the fluid. The ends of a vortex must reach to some boundary, inside or outside the fluid. A vortex which is bent round so that its opposite ends join is capable of existing, but no vortex has a free end in the fluid. The fluid round the vortex is always in motion, and one produces a definite movement in another. Lord Kelvin has proposed the hypothesis that portions of a fluid segregated in vortices account for the origin of matter. The properties of the ether in respect of its capacity of propagating disturbances can be explained by the assumption of vortices in it, instead of by a property of rigidity. It is difficult to conceive, however, of any arrangement of the vortex rings and endless vortex filaments in the ether. Now, the further consideration of four-dimensional rotations shows the existence of a kind of vortex which would make an ether filled with a homogeneous vortex motion easily thinkable. To understand the nature of this vortex, we must go on and take a step by which we accept the full significance of the four-dimensional hypothesis. Granted four-dimensional axes, we have seen that a rotation of one into another leaves two unaltered, and these two form the axial plane about which the rotation takes place. But what about these two? Do they necessarily remain motionless? There is nothing to prevent a rotation of these two, one into the other, taking place concurrently with the first rotation. This possibility of a double rotation deserves the most careful attention, for it is the kind of movement which is distinctly typical of four dimensions. Rotation round a plane is analogous to rotation round an axis, but in three-dimensional space there is no motion analogous to the double rotation, in which, while axis 1 changes into axis 2, axis 3 changes into axis 4. Consider a four-dimensional body with four independent axes x, y, z, w. A point in it can move in only one direction at a given moment. If the body has a velocity of rotation by which the x-axis changes into the y-axis, and all parallel sections move in a similar manner, then the point will describe a circle. If now, in addition to the rotation by which the x-axis changes into the y-axis, the body has a rotation by which the z-axis turns into the w-axis, the point in question will have a double motion in consequence of the two turnings. The motions will compound, and the point will describe a circle, but not the same circle which it would describe in virtue of either rotation separately. We know that if a body in three-dimensional space is given two movements of rotation, they will combine into a single movement of rotation round a definite axis. It is in no different condition from that in which it is subjected to one movement of rotation. The direction of the axis changes, that is all. The same is not true about a four-dimensional body. The two rotations, x to y and z to w, are independent. A body subject to the two is in a totally different condition to that which it is in when subject to one only. When subject to a rotation such as that of x to y, a whole plane in the body, as we have seen, is stationary. When subject to the double rotation, no part of the body is stationary except the point common to the two planes of rotation. If the two rotations are equal in velocity, every point in the body describes a circle. All points equally distant from the stationary point describe circles of equal size. We can represent a four-dimensional sphere by means of two diagrams, in one of which we take the three axes x, y, z, in the other the axes x, w, and z. In figure 13 we have the view of a four-dimensional sphere in the space of x, y, z. Figure 13 shows all that we can see of the four-sphere in the space of x, y, z, for it represents all the points in that space which are at an equal distance from the centre. Let us now take the xz section and let the axis of w take the place of the y-axis. Here, in figure 14, we have the space of xzw. In this space we have to take all the points which are at the same distance from the centre. Consequently, we have another sphere. If we had a three-dimensional sphere, as has been shown before, we should have merely a circle in the xzw space, the xz circle seen in the space of xzw. But now, taking the view in the space of xzw, we have a sphere in that space also. In a similar manner, whichever set of three axes we take, we obtain a sphere. In figure 13, Let us imagine the rotation in the direction xy to be taking place. The point x will turn to y, and p to p'. The axis z, z' remains stationary, and this axis is all of the plane ZW which we can see in the space section exhibited in the figure. In figure 14, imagine the rotation from Z to W to be taking place. The W axis now occupies the position previously occupied by the Y axis. This does not mean that the W axis can coincide with the Y axis. It indicates that we are looking at the four-dimensional sphere from a different point of view. Any three-space view will show us three axes, and in figure 14 we are looking at XZW. The only part that is identical in the two diagrams is the circle of the x and z axes, which axes are contained in both diagrams. Thus the plane ZXZ' is the same in both, and the point P represents the same point in both diagrams. Now, in figure 14, let the ZW rotation take place. The z-axis will turn towards the point W of the w-axis, and the point P will move in a circle about the point X. Thus, in figure 13, the point P moves in a circle parallel to the xy plane. In figure 14, it moves in a circle parallel to the ZW plane, indicated by the arrow. Now, suppose both of these independent rotations compounded. The point P will move in a circle, but this circle will coincide with neither of the circles in which either one of the rotations will take it. The circle the point P will move in will depend on its position on the surface of the force sphere. In this double rotation, possible in four-dimensional space, there is a kind of movement totally unlike any with which we are familiar in three-dimensional space. It is a requisite preliminary to the discussion of the behaviour of the small particles of matter, with a view to determining whether they show the characteristics of four-dimensional movements, to become familiar with the main characteristics of this double rotation. And here I must rely on a formal and logical assent, rather than on the intuitive apprehension, which can only be obtained by a more detailed study. In the first place, this double rotation consists in two varieties or kinds, which we will call the A and B kinds. Consider four axes x, y, z, w. The rotation of x to y can be accompanied with the rotation of z to w. Call this the A kind. But also the rotation of x to y can be accompanied by the rotation of not z to w, but w to z. Call this the B kind. They differ in only one of the component rotations. One is not the negative of the other. It is the semi-negative. The opposite of an x to y, z to w rotation would be y to x, w to z. The semi-negative is x to y and w to z. If four dimensions exist, and we cannot perceive them, because the extension of matter is so small in the fourth dimension that all movements are withheld from direct observation except those which are three-dimensional, we should not observe these double rotations, but only the effects of them in three-dimensional movements of the type with which we are familiar. If matter in its small particles is four-dimensional, we should expect this double rotation to be a universal characteristic of the atoms and molecules, for no portion of matter is at rest. The consequences of this corpuscular motion can be perceived, but only under the form of ordinary rotation or displacement. Thus, if the theory of four dimensions is true, we have in the corpuscles of matter a whole world of movement which we can never study directly, but only by means of inference. The rotation A, as I have defined it, consists of two equal rotations, one about the plane of ZW, the other about the plane of XY. It is evident that these rotations are not necessarily equal. A body may be moving with a double rotation, in which these two independent components are not equal, but in such a case we can consider the body to be moving with a composite rotation, a rotation of the A or B kind, and in addition a rotation about a plane. If we combine an A and a B movement, we obtain a rotation about a plane, for the first being x to y and z to w, and the second being x to y and w to z, when they are put together, the z to w and w to z rotations neutralise each other, and we obtain an x to y rotation only, which is a rotation about the plane of zw. Similarly, if we take a b rotation, y to x and z to w, we get, on combining this with the a rotation, a rotation of z to w about the xy plane. In this case, the plane of rotation is in the three-dimensional space of x, y, z, and we have, what has been described before, a twisting about a plane in our space. Consider now a portion of a perfect liquid having an A motion. It can be proved that it possesses the properties of a vortex. It forms a permanent individuality, a separated out portion of the liquid, accompanied by a motion of the surrounding liquid. It has properties analogous to those of a vortex filament, but it is not necessary for its existence that its ends should reach the boundary of the liquid. It is self-contained, and, unless disturbed, is circular in every section. If we suppose the ether to have its properties of transmitting vibration given it by such vortices, we must inquire how they lie together in four-dimensional space. Placing a circular disc on a plane, and surrounding it by 6 others, we find that if the central one is given a motion of rotation, it imparts to the others a rotation which is antagonistic in every 2 adjacent ones. Reader's note, figure 15, end reader's note. If A goes round, as shown by the arrow, B and C will be moving in opposite ways, and each tends to destroy the motion of the other. Now, if we suppose spheres to be arranged in a corresponding manner in three-dimensional space, they will be grouped in figures which are for three-dimensional space what hexagons are for plane space. If a number of spheres of soft clay be pressed together so as to fill up the interstices, each will assume the form of a 14-sided figure called a tetrachidecagon. Now, assuming space to be filled with such tetrachidecagon's, and placing a sphere in each, it will be found that one sphere is touched by 8 others. The remaining 6 spheres of the 14 which surround the central one will not touch it, but will touch 3 of those in contact with it. Hence, if the central sphere rotates, it will not necessarily drive those around it so that their motions will be antagonistic to each other, but the velocities will not arrange themselves in a systematic manner. In four-dimensional space, the figure which forms the next term of the series, hexagon tetrachidecagon, is a 30-sided figure. It has for its faces 10 solid tetrachidecagon's and 20 hexagonal prisms. Such figures will exactly fill four-dimensional space, 5 of them meeting at every point. If now in each of these figures we suppose a solid four-dimensional sphere to be placed, any one sphere is surrounded by 30 others. Of these it touches 10, and if it rotates, it drives the rest by means of these. Now, if we imagine the central sphere to be given an A or a B rotation, it will turn the whole mass of spheres round in a systematic manner. Suppose four-dimensional space to be filled with such spheres, each rotating with a double rotation. The whole mass would form one consistent system of motion, in which each one drove every other one, with no friction or lagging behind. Every sphere would have the same kind of rotation. In three-dimensional space, if one body drives another round, the second body rotates with the opposite kind of rotation. But in four-dimensional space, these four-dimensional spheres would each have the double negative of the rotation of the one next it. And we have seen that the double negative of an A or B rotation is still an A or B rotation. Thus, four-dimensional space could be filled with a system of self-preservative living energy. If we imagine the four-dimensional spheres to be of liquid and not of solid matter, then even if the liquid were not quite perfect, and there were a slight retarding effect of one vortex on another, the system would still maintain itself. In this hypothesis, we must look on the ether as possessing energy, and its transmission of vibrations not as the conveying of a motion imparted from without, but as a modification of its own motion. We are now in possession of some of the conceptions of four-dimensional mechanics, and will turn aside from the line of their development to inquire if there is any evidence of their applicability to the processes of nature. Is there any mode of motion in the region of the minute which, giving three-dimensional movements for its effect, still in itself escapes the grasp of our mechanical theories? I would point to electricity. Through the labours of Faraday and Maxwell, we are convinced that the phenomena of electricity are of the nature of the stress and strain of a medium, but there is still a gap to be bridged over in their explanation. The laws of elasticity which Maxwell assumes are not those of ordinary matter. And to take another instance, a magnetic pole in the neighbourhood of a current tends to move. Maxwell has shown that the pressures on it are analogous to the velocities in a liquid which would exist if a vortex took the place of the electric current. But we cannot point out the definite mechanical explanation of these pressures. There must be some mode of motion of a body or of the medium, in virtue of which a body is said to be electrified. Take the ions which convey charges of electricity 500 times greater in proportion to their mass than are carried by the molecules of hydrogen in electrolysis. In respect of what motion can these ions be said to be electrified? It can be shown that the energy they possess is not energy of rotation. Think of a short rod rotating. If it is turned over, it is found to be rotating in the opposite direction. Now, if rotation in one direction corresponds to positive electricity, rotation in the opposite direction corresponds to negative electricity, and the smallest electrified particles would have their charges reversed by being turned over, an absurd supposition. If we fix on a mode of motion as a definition of electricity, we must have two varieties of it, one for positive and one for negative, and a body possessing the one kind must not become possessed of the other by any change in its position. All three-dimensional motions are compounded of rotations and translations, and none of them satisfy this first condition for serving as a definition of electricity. But consider the double rotation of the A and B kinds. A body rotating with the A motion cannot have its motion transformed into the B kind by being turned over in any way. Suppose a body has the rotation x to y and z to w. Turning it about the xy plane, we reverse the direction of the motion x to y, but we also reverse the z to w motion, for the point at the extremity of the positive z-axis is now at the extremity of the negative z-axis, and since we have not interfered with its motion, it goes in the direction of position w. Hence we have y to x and w to z, which is the same as x to y and z to w. Thus both components are reversed, and there is the A motion over again. The B kind is the semi-negative, with only one component reversed. Hence a system of molecules with the A motion would not destroy it in one another, and would impart it to a body in contact with them. Thus A and B motions possess the first requisite which must be demanded in any mode of motion representative of electricity. Let us trace out the consequences of defining positive electricity as an A motion and negative electricity as a B motion. The combination of positive and negative electricity produces a current. Imagine a vortex in the ether of the A kind, and unite with this one of the B kind. An A motion and B motion produce rotation round a plane, which is in the ether a vortex round an axial surface. It is a vortex of the kind we represent as a part of a sphere turning inside out. Now such a vortex must have its rim on a boundary of the ether, on a body in the ether. Let us suppose that a conductor is a body which has the property of serving as the terminal abutment of such a vortex. Then the conception we must form of a closed current is of a vortex sheet having its edge along the circuit of the conducting wire. The whole wire will then be like the centres on which a spindle turns in three-dimensional space, and any interruption of the continuity of the wire will produce a tension in place of a continuous revolution. As the direction of the rotation of the vortex is from a three-space direction into the fourth dimension and back again, there will be no direction of flow to the current, but it will have two sides, according to whether Z goes to W or Z goes to negative W. We can draw any line from one part of the circuit to another. Then the ether along that line is rotating round its points. This geometric image corresponds to the definition of an electric circuit. It is known that the action does not lie in the wire, but in the medium, and it is known that there is no direction of flow in the wire. No explanation has been offered in three-dimensional mechanics of how an action can be impressed throughout a region and yet necessarily run itself out along a closed boundary, as is the case in an electric current. But this phenomenon corresponds exactly to the definition of a four-dimensional vortex. If we take a very long magnet, so long that one of its poles is practically isolated, and put this pole in the vicinity of an electric circuit, we find that it moves. Now, assuming for the sake of simplicity that the wire which determines the current is in the form of a circle, if we take a number of small magnets and place them all pointing in the same direction, normal to the plane of the circle, so that they fill it and the wire binds them round, we find that this sheet of magnets has the same effect on the magnetic pole that the current has. The sheet of magnets may be curved, but the edge of it must coincide with the wire. The collection of magnets is then equivalent to the vortex sheet, and an elementary magnet to a part of it. Thus, we must think of a magnet as conditioning a rotation in the ether round the plane which bisects at right angles the line joining its poles. If a current is started in a circuit, we must imagine vortices like bowls turning themselves inside out, starting from the contour. In reaching a parallel circuit, if the vortex sheet were interrupted and joined momentarily to the second circuit by a free rim, the axis plane would lie between the two circuits, and a point on the second circuit opposite a point on the first would correspond to a point opposite to it on the first. Hence we should expect a current in the opposite direction in the second circuit. Thus the phenomena of induction are not inconsistent with the hypothesis of a vortex about an axial plane. In four-dimensional space, in which all four dimensions were commensurable, the intensity of the action transmitted by the medium would vary inversely as the cube of the distance. Now the action of a current on a magnetic pole varies inversely as the square of the distance. Hence, over measurable distances, the extension of the ether in the fourth dimension cannot be assumed as other than small in comparison with those distances. If we suppose the ether to be filled with vortices in the shape of four-dimensional spheres rotating with the A motion, the B motion would correspond to electricity in the one-fluid theory. There would thus be a possibility of electricity existing in two forms, statically, by itself, and, combined with the universal motion, in the form of a current. To arrive at a definite conclusion, it will be necessary to investigate the resultant pressures which accompany the co-location of solid vortices with surface ones. To recapitulate, the movements and mechanics of four-dimensional space are definite and intelligible. A vortex with a surface as its axis affords a geometric image of a closed circuit, and there are rotations which, by their polarity, afford a possible definition of statical electricity. Footnote: these double rotations of the A and B kinds I should like to call Hamiltons and co-Hamiltons, for it is a singular fact that in his Quaternions Sir William Rowan Hamilton has given the theory of either the A or the B kind. They follow the laws of his symbols, I, J, K. Hamiltons and co-Hamiltons seem to be natural units of geometrical expression. In the paper in the Proceedings of the Royal Irish Academy, November 1903, already alluded to, I have shown something of the remarkable facility which is gained in dealing with the composition of 3- and 4-dimensional rotations by an alteration in Hamilton's notation, which enables his system to be applied to both the A and B kinds of rotations. The objection which has been often made to Hamilton's system, namely that it is only under special conditions of application that his processes give geometrically interpretable results, can be removed if we assume that he was really dealing with a 4-dimensional motion, and alter his notations to bring this circumstance into explicit recognition. End footnote. End of section 25. Section 26 of The Fourth Dimension by Charles Howard Hinton. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Appendix 1, Part 1. The Models. In Chapter 11 a description has been given which will enable anyone to make a set of models illustrative of the tesseract and its properties. The set here supposed to be employed consists of 1. 3 sets of 27 cubes each, 2. 27 slabs, 3. 12 cubes with points, lines, faces distinguished by colours, which will be called the catalogue cubes. The preparation of the 12 catalogue cubes involves the expenditure of a considerable amount of time. It is advantageous to use them, but they can be replaced by the drawing of the views of the tesseract, or by a reference to figures 103, 104, 105, 106 of the text. The slabs are coloured like the 27 cubes of the first cubic block in figure 101, the one with red, white, yellow axes. The colours of the 3 sets of 27 cubes are those of the cubes shown in figure 101. The slabs are used to form the representation of a cube in a plane, and can well be dispensed with by anyone who is accustomed to deal with solid figures. But the whole theory depends on a careful observation of how the cube would be represented by these slabs. In the first step, that of forming a clear idea how a plane being would represent 3-dimensional space, only one of the catalogue cubes and one of the 3 blocks is needed. Application to the step from plane to solid. Look at figure 1 of the views of the tesseract, or, what comes to the same thing, take catalogue cube number 1 and place it before you, with the red line running up, the white line running to the right, the yellow line running away. The 3 dimensions of space are then marked out by these lines or axes. Now take a piece of cardboard or a book and place it so that it forms a wall extending up and down, not opposite to you, but running away parallel to the wall of the room on your left hand. Placing the catalogue cube against this wall, we see that it comes into contact with it by the red and yellow lines, and by the included orange face. In the plane being's world, the aspect he has of the cube would be a square surrounded by red and yellow lines with grey points. Now, keeping the red line fixed, turn the cube about it so that the yellow line goes out to the right and the white line comes into contact with the plane. In this case, a different aspect is presented to the plane being, a square, namely, surrounded by red and white lines and grey points. You should particularly notice that when the yellow line goes out at right angles to the plane and the white comes in, the latter does not run in the same sense that the yellow did. From the fixed grey point at the base of the red line, the yellow line ran away from you. The white line now runs towards you. This turning at right angles makes the line which was out of the plane before come into it in an opposite sense to that in which the line ran which has just left the plane. If the cube does not break through the plane, this is always the rule. Again, turn the cube back to the normal position, with red running up, white to the right, and yellow away, and try another turning. You can keep the yellow line fixed and turn the cube about it. In this case, the red line going out to the right, the white line will come in, pointing downwards. You will be obliged to elevate the cube from the table in order to carry out this turning, It is always necessary, when a vertical axis goes out of a space, to imagine a movable support which will allow the line which ran out before to come in below. Having looked at the three ways of turning the cube so as to present different faces to the plane, examine what would be the appearance if a square hole were cut in the piece of cardboard and the cube were to pass through it. A hole can be actually cut, and it will be seen that in the normal position, with red axis running up, yellow away, and white to the right, the square first perceived by the plane being, the one contained by red and yellow lines, would be replaced by another square, of which the line towards you is pink, the section line of the pink face. The line above is light yellow, below is light yellow, and on the opposite side away from you is pink. In the same way, the cube can be pushed through a square opening in the plane from any of the positions which you have already turned it into. In each case, the plane being will perceive a different set of contour lines. Having observed these facts about the catalogue cube, turn now to the first block of 27 cubes. You notice that the colour scheme on the catalogue cube and that of this set of blocks is the same. Place them before you. A grey or null cube on the table, above it a red cube, and on the top a null cube again. Then away from you place a yellow cube, and beyond it a null cube. Then to the right place a white cube, and beyond it another null. Then complete the block according to the scheme of the catalogue cube, putting in the centre of all an ochre cube. You have now a cube like that which is described in the text. For the sake of simplicity, in some cases this cubic block can be reduced to one of 8 cubes by leaving out the terminations in each direction. Thus, instead of null, red, null, 3 cubes, you can take null, red, 2 cubes, and so on. It is useful, however, to practice the representation in a plane of a block of 27 cubes. For this purpose, take the slabs and build them up against the piece of cardboard or the book in such a way as to represent the different aspects of the cube. Proceed as follows. First, cube in normal position. Place 9 slabs against the cardboard to represent the 9 cubes in the wall of the red and yellow axes facing the cardboard. These represent the aspect of the cube as it touches the plane. Now, push these along the cardboard and make a different set of 9 slabs to represent the appearance which the cube would present to a plane being if it were to pass halfway through the plane. There would be a white slab, above it a pink one, above that another white one, and 6 others, representing what would be the nature of a section across the middle of the block of cubes. The section can be thought of as a thin slice cut out by 2 parallel cuts across the cube. Having arranged these 9 slabs, push them along the plane, and make another set of 9 to represent what would be the appearance of the cube when it had almost completely gone through. This set of 9 will be the same as the first set of 9. Now we have in the plane 3 sets of 9 slabs each, which represent 3 sections of the 27 block. They are put alongside one another. We see that it does not matter in what order the sets of 9 are put. As the cube passes through the plane, they represent appearances which follow, the one after the other. If they were what they represented, they could not exist in the same plane together. This is a rather important point, namely, to notice that they should not coexist on the plane, and that the order in which they are placed is indifferent. When we represent a 4-dimensional body, our solid cubes are to us in the same position that the slabs are to the plane being. You should also notice that each of these slabs represents only the very thinnest slice of a cube. The set of 9 slabs first set up represents the side surface of the block. It is, as it were, a kind of tray, a beginning from which the solid cube goes off. The slabs, as we use them, have thickness, but this thickness is a necessity of construction. They are to be thought of as merely of the thickness of a line. If now the block of cubes passed through the plane at the rate of an inch a minute, the appearance to a plane being would be represented by 1. The first set of 9 slabs lasting for 1 minute, 2. The second set of 9 slabs lasting for 1 minute, 3. The third set of 9 slabs lasting for 1 minute. Now the appearances which the cube would present to the plane being in other positions can be shown by means of these slabs. The use of such slabs would be the means by which a plane being could acquire a familiarity with our cube. Turn the catalogue cube, or imagine the coloured figure turned, so that the red line runs up, the yellow line out to the right, and the white line towards you. Then turn the block of cubes to occupy a similar position. The block has now a different wall in contact with the plane. Its appearance to a plane being will not be the same as before. He has, however, enough slabs to represent this new set of appearances, but he must remodel his former arrangement of them. He must take a null, a red, and a null slab from the first of his sets of slabs, then a white, a pink, and a white from the second, and then a null, a red, and a null from the third set of slabs. He takes the first column from the first set, the first column from the second set, and the first column from the third set. To represent the halfway through appearance, which is as if a very thin slice were cut out halfway through the block, he must take the second column of each of his sets of slabs, and, to represent the final appearance, the third column of each set. Now turn the catalogue cube back to the normal position, and also the block of cubes. There is another turning, a turning about the yellow line, in which the white axis comes below the support. You cannot break through the surface of the table, so you must imagine the old support to be raised. Then the top of the block of cubes in its new position is at the level at which the base of it was before. Now, representing the appearance on the plane, we must draw a horizontal line to represent the old base. The line should be drawn 3 inches high on the cardboard. Below this, the representative slabs can be arranged. It is easy to see what they are. The old arrangements have to be broken up and the layers taken in order. The first layer of each for the representation of the aspect of the block as it touches the plane. Then the second layers will represent the appearance halfway through, and the third layers will represent the final appearance. It is evident that the slabs individually do not represent the same portion of the cube in these different presentations. In the first case, each slab represents a section or a face perpendicular to the white axis. In the second case, a face or a section which runs perpendicularly to the yellow axis. And in the third case, a section or a face perpendicular to the red axis. But by means of these 9 slabs, the plane being can represent the whole of the cubic block. He can touch and handle each portion of the cubic block. There is no part of it which he cannot observe. Taking it bit by bit, 2 axes at a time, he can examine the whole of it. End of section 26. Section 27 of The Fourth Dimension by Charles Howard Hinton. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Appendix 1. The Models. Part 2. Our representation of a block of tesseracts. Look at the views of the tesseract 1, 2, 3, or take the catalogue cubes 1, 2, 3, and place them in front of you in any order, say running from left to right, placing one in the normal position, the red axis running up, the white to the right, and yellow away. Now notice that in catalogue cube 2, the colours of each region are derived from those of the corresponding region of cube 1 by the addition of blue. Thus, null plus blue equals blue, and the corners of number 2 are blue. Again, red plus blue equals purple, and the vertical lines of 2 are purple. Blue plus yellow equals green, and the line which runs away is coloured green. By means of these observations you may be sure that catalogue cube 2 is rightly placed. Catalogue cube 3 is just like number 1. Having these cubes in what we may call their normal position, proceed to build up the 3 sets of blocks. This is easily done in accordance with the colour scheme on the catalogue cubes. The first block we already know. Build up the second block, beginning with a blue corner cube, placing a purple on it, and so on. Having these 3 blocks, we have the means of representing the appearances of a group of 81 tesseracts. Let us consider a moment what the analogy in the case of the plane being is. He has his 3 sets of 9 slabs each. We have our 3 sets of 27 cubes each. Our cubes are like his slabs. As his slabs are not the things which they represent to him, so our cubes are not the things they represent to us. The plane being's slabs are to him the faces of cubes. Our cubes, then, are the faces of tesseracts, the cubes by which they are in contact with our space. As each set of slabs in the case of the plane being might be considered as a sort of tray from which the solid contents of the cubes came out, so our 3 blocks of cubes may be considered as 3-space trays, each of which is the beginning of an inch of the solid contents of the 4-dimensional solids starting from them. We want now to use the names null, red, white, etc. for tesseracts. The cubes we use are only tesseract faces. Let us denote that fact by calling the cube of null colour null face, or shortly null F, meaning that it is the face of a tesseract. To determine which face it is, let us look at the catalogue cube 1, or the first of the views of the tesseract, which can be used instead of the models. It has 3 axes, red, white, yellow, in our space. Hence, the cube determined by these axes is the face of the tesseract which we now have before us. It is the ochre face. It is enough, however, simply to say null F, red F for the cubes which we use. To impress this in your mind, imagine that tesseracts do actually run from each cube. Then, when you move the cubes about, you move the tesseracts about with them. You move the face, but the tesseract follows with it, as the cube follows when its face is shifted in a plane. The cube null in the normal position is the cube which has in it the red, yellow, white axes. It is the face having these, but wanting the blue. In this way you can define which face it is you are handling. I will write an F after the name of each tesseract, just as the plane being might call each of his slabs null slab, yellow slab, etc., to denote that they were representations. We have then in the first block of 27 cubes the following: null F, red F, null F, going up, white F, null F, lying to the right, and so on. Starting from the null point and travelling up 1 inch, we are in the null region, the same for the away and the right hand directions. And if we were to travel in the 4th dimension for 1 inch, we should still be in a null region. The tesseract stretches equally all 4 ways. Hence, the appearance we have in this first block would do equally well if the tesseract block were to move across our space for a certain distance. For anything less than 1 inch of their transverse motion, we should still have the same appearance. You must notice, however, that we should not have null face after the motion had begun. When the tesseract, null for instance, had moved ever so little, we should not have a face of null, but a section of null in our space. Hence, when we think of the motion across our space, we must call our cubes tesseract sections. Thus, on null passing across, we should see first null F, then null S, and then finally null F again. Imagine now the whole first block of 27 tesseracts to have moved transverse to our space a distance of 1 inch. Then the second set of tesseracts, which originally were 1 inch distant from our space, would be ready to come in. Their colours are shown in the second block of 27 cubes which you have before you. These represent the tesseract faces of the set of tesseracts that lay before 1 inch away from our space. They are ready now to come in, and we can observe their colours. in the place which null F occupied before, we have blue F. In place of red F, we have purple F, and so on. Each tesseract is coloured like the one whose place it takes in this motion, with the addition of blue. Now, if the tesseract block goes on moving at the rate of an inch a minute, this next set of tesseracts will occupy a minute in passing across. We shall see, to take the null one, for instance, first of all null face, then null section, then null face again. At the end of the second minute, the second set of tesseracts has gone through, and the third set comes in. This, as you see, is coloured just like the first. Altogether, these three sets extend 3 inches in the fourth dimension, making the tesseract block of equal magnitude in all dimensions. We have now before us a complete catalogue of all the tesseracts in our group. We have seen them all, and we shall refer to this arrangement of the blocks as the normal position. We have seen as much of each tesseract at a time as could be done in a 3-dimensional space. Each part of each tesseract has been in our space, and we could have touched it. The fourth dimension appeared to us as the duration of the block. If a bit of our matter were to be subjected to the same motion, it would be instantly removed out of our space. Being thin in the fourth dimension, it is at once taken out of our space by a motion in the fourth dimension. But the tesseract block we represent, having length in the fourth dimension, remains steadily before our eyes for 3 minutes when it is subjected to this transverse motion. We have now to form representations of the other views of the same tesseract group which are possible in our space. Let us then turn the block of tesseracts so that another face of it comes into contact with our space, and then by observing what we have and what changes come when the block traverses our space, we shall have another view of it. The dimension which appeared as duration before will become extension in one of our known dimensions, and a dimension which coincided with one of our space dimensions will appear as duration. Leaving catalogue cube 1 in the normal position, remove the other two, or suppose them removed. We have in space the red, the yellow, and the white axes. Let the white axis go out into the unknown and occupy the position the blue axis holds. Then the blue axis, which runs in that direction now, will come into space. But it will not come in pointing in the same way that the white axis does now. It will point in the opposite sense. It will come in running to the left instead of running to the right as the white axis does now. When this turning takes place, every part of the cube 1 will disappear except the left-hand face, the orange face, and the new cube that appears in our space will run to the left from this orange face, having axes red, yellow, blue. Take models 4, 5, 6. Place 4, or suppose number 4 of the tesseract views placed, with its orange face coincident with the orange face of 1. Red line to red line and yellow line to yellow line, with the blue line pointing to the left. Then remove cube 1, and we have the tesseract face, which comes in when the white axis runs in the positive unknown, and the blue axis comes into our space. Now, place catalogue cube 5 in some position. It does not matter which, say to the left, and place it so that there is a correspondence of colour corresponding to the colour of the line that runs out of space. The line that runs out of space is white. Hence, every part of this cube 5 should differ from the corresponding part of 4 by an alteration in the direction of white. Thus we have white points in 5 corresponding to the null points in 4. We have a pink line corresponding to a red line, a light yellow line corresponding to a yellow line, an ochre face corresponding to an orange face. This cube section is completely named in chapter 11. Finally, cube 6 is a replica of 1. These catalogue cubes will enable us to set up our models of the block of tesseracts. First of all for the set of tesseracts, which, beginning in our space, reach out 1 inch in the unknown, we have the pattern of catalogue cube 4. We see that we can build up a block of 27 tesseract faces after the colour scheme of cube 4 by taking the left-hand wall of block 1, then the left-hand wall of block 2, and finally that of block 3. We take, that is, the first 3 walls of our previous arrangement to form the first cubic block of this new one. This will represent the cubic faces by which the group of tesseracts in its new position touches our space. We have, running up, null F, red F, null F. In the next vertical line on the side remote from us, we have yellow F, orange F, yellow F, and then the first colours over again. Then the 3 following columns are blue F, purple F, blue F, green F, brown F, green F, blue F, purple F, blue F. The last 3 columns are like the first. These tesseracts touch our space, and none of them are by any part of them distant more than an inch from it. What lies beyond them in the unknown? This can be told by looking at catalogue cube 5. According to its scheme of colour, we see that the second wall of each of our old arrangements must be taken. Putting them together, we have as the corner white F, above it pink F, above it white F. The column next to this, remote from us, is as follows: light yellow F, ochre F, light yellow F, and beyond this a column like the first. Then for the middle of the block, light blue F, above it light purple, then light blue. The centre column has at the bottom light green F, light brown F in the centre, and at the top light green F. The last wall is like the first. The third block is made by taking the third walls of our previous arrangement, which we called the normal one. You may ask what faces and what sections our cubes represent. To answer this question, look at what axes you have in our space. You have red, yellow, blue. Now these determine brown. The colours red, yellow, blue are supposed by us, when mixed, to produce a brown colour. And that cube which is determined by the red, yellow, blue axes we call the brown cube. When the tesseract block in its new position begins to move across our space, each tesseract in it gives a section in our space. This section is transverse to the white axis, which now runs in the unknown. As the tesseract in its present position passes across our space, we should see first of all the first of the blocks of cubic faces we have put up. These would last for a minute, then would come the second block, and then the third. At first we should have a cube of tesseract faces, each of which would be brown. Directly the movement began, we should have tesseract sections transverse to the white line. There are 2 more analogous positions in which the block of tesseracts can be placed. To find the third position, restore the blocks to the normal arrangement. Let us make the yellow axis go out into the positive unknown, and let the blue axis, consequently, come in running towards us. The yellow ran away, so the blue will come in running towards us. Put catalogue cube 1 in its normal position. Take catalogue cube 7 and place it so that its pink face coincides with the pink face of cube 1, making also its red axis coincide with the red axis of 1 and its white with the white. Moreover, make cube 7 come towards us from cube 1. Looking at it, we see in our space red, white and blue axes. The yellow runs out. Place catalogue cube 8 in the neighbourhood of 7. Observe that every region in 8 has a change in the direction of yellow from the corresponding region in 7. This is because it represents what you come to now in going in the unknown, when the yellow axis runs out of our space. Finally, catalogue cube 9, which is like number 7, shows the colours of the third set of tesseracts. Now evidently, starting from the normal position, to make up our 3 blocks of tesseract faces, we have to take the near wall from the first block, the near wall from the second, and then the near wall from the third block. This gives us the cubic block formed by the faces of the 27 tesseracts, which are now immediately touching our space. Following the colour scheme of catalogue cube 8, we make the next set of 27 tesseract faces, representing the tesseracts, each of which begins 1 inch off from our space, by putting the second walls of our previous arrangement together, and the representation of the third set of tesseracts is the cubic block formed of the remaining 3 walls. Since we have red, white, blue axes in our space to begin with, the cubes we see at first are light purple tesseract faces, and after the transverse motion begins, we have cubic sections transverse to the yellow line. Restore the blocks to the normal position. There remains the case in which the red axis turns out of space. In this case, the blue axis will come in downwards, opposite to the sense in which the red axis ran. In this case, take catalogue cubes 10, 11, 12. Lift up catalogue cube 1 and put 10 underneath it, imagining that it goes down from the previous position of 1. We have to keep in space the white and the yellow axes, and let the red go out, the blue come in. Now, you will find on cube 10 a light yellow face. This should coincide with the base of 1, and the white and yellow lines on the two cubes should coincide. Then, the blue axis running down, you have the catalogue cube correctly placed, and it forms a guide for putting up the first representative block. Catalogue cube 11 will represent what lies in the fourth dimension. Now the red line runs in the fourth dimension. Thus the change from 10 to 11 should be towards red. Corresponding to a null point is a red point, to a white line is a pink line, to a yellow line an orange line, and so on. Catalogue cube 12 is like 10. Hence, we see that to build up our blocks of tesseract faces, we must take the bottom layer of the first block, hold that up in the air, underneath it place the bottom layer of the second block, and finally underneath this last, the bottom layer of the last of our normal blocks. Similarly, we make the second representative group by taking the middle courses of our three blocks. The last is made by taking the three topmost layers. The three axes in our space before the transverse motion begins are blue, white, yellow, so we have light green tesseract faces, and after the motion begins, sections transverse to the red line. These three blocks represent the appearances as the tesseract group in its new position passes across our space. The cubes of contact in this case are those determined by the three axes in our space, namely the white, the yellow, the blue. Hence they are light green. It follows from this that light green is the interior cube of the first block of representative cubic faces. Practice in the manipulations described, with the realization in each case of the face or section which is in our space, is one of the best means of a thorough comprehension of the subject. We have to learn how to get any part of these four-dimensional figures into space, so that we can look at them. We must first learn to swing a tesseract and a group of tesseracts about in any way. When these operations have been repeated, and the method of arrangement of the set of blocks has become familiar, it is a good plan to rotate the axes of the normal cube 1 about a diagonal, and then repeat the whole series of turnings. Thus, in the normal position, red goes up, white to the right, yellow away. Make white go up, yellow to the right, and red away. Learn the cube in this position by putting up the set of blocks of the normal cube over and over again, till it becomes as familiar to you as in the normal position. Then, when this is learned and the corresponding changes in the arrangement of the tesseract groups are made, another change should be made. Let, in the normal cube, yellow go up, red to the right and white away. Learn the normal block of cubes in this new position by arranging them and rearranging them till you know without thought where each one goes. Then carry out all the tesseract arrangements and turnings. If you want to understand the subject, but do not see your way clearly, if it does not seem natural and easy to you, practice these turnings. Practice, first of all, the turning of a block of cubes round, so that you know it in every position, as well as in the normal one. Practice by gradually putting up the set of cubes in their new arrangements. Then put up the tesseract blocks in their arrangements. This will give you a working conception of higher space. You will gain the feeling of it, whether you take up the mathematical treatment of it or not. End of section 27. Section 28 of The Fourth Dimension by Charles Howard Hinton. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Appendix 2. A language of space. The mere naming the parts of the figures we consider involves a certain amount of time and attention. This time and attention leads to no result, for with each new figure the nomenclature applied is completely changed. Every letter or symbol is used in a different significance. Surely it must be possible in some way to utilize the labour thus at present wasted. Why should we not make a language for space itself, so that every position we want to refer to would have its own name? Then, every time we named a figure in order to demonstrate its properties, we should be exercising ourselves in the vocabulary of place. If we use a definite system of names and always refer to the same space position by the same name, we create, as it were, a multitude of little hands, each prepared to grasp a special point, position, or element, and hold it for us in its proper relations. We make, to use another analogy, a kind of mental paper which has somewhat of the properties of a sensitive plate, in that it will register without effort complex visual or tactual impressions. But of far more importance than the applications of a space language to the plane and to solid space is the facilitation it brings with it to the study of four-dimensional shapes. I have delayed introducing a space language because all the systems I made turned out, after giving them a fair trial, to be intolerable. I have now come upon one which seems to present features of permanence, and I will here give an outline of it, so that it can be applied to the subject of the text, and in order that it may be subjected to criticism. The principle on which the language is constructed is to sacrifice every other consideration for brevity. It is indeed curious that we are able to talk and converse on every subject of thought except the fundamental one of space. The only way of speaking about the spatial configurations that underlie every subject of discursive thought is a coordinate system of numbers. This is so awkward and incommodious that it is never used. In thinking also, in realizing shapes, we do not use it. We confine ourselves to a direct visualization. Now, the use of words corresponds to the storing up of our experiences in a definite brain structure. A child, in the endless tactile, visual, mental manipulations it makes for itself, is best left to itself. But in the course of instruction, the introduction of space names would make the teacher's work more cumulative and the child's knowledge more social. Their full use can only be appreciated if they are introduced early in the course of education, but in a minor degree anyone can convince himself of their utility, especially in our immediate subject of handling four-dimensional shapes. The sum total of the results obtained in the preceding pages can be compendiously and accurately expressed in 9 words of the space language. In one of Plato's dialogues, Socrates makes an experiment on a slave boy standing by. He makes certain perceptions of space awake in the mind of Meno's slave by directing his close attention on some simple facts of geometry. By means of a few words and some simple forms, we can repeat Plato's experiment on new ground. Do we, by directing our close attention on the facts of 4 dimensions, awaken a latent faculty in ourselves? The old experiment of Plato's, it seems to me, has come down to us as novel as on the day he incepted it, and its significance not better understood through all the discussion of which it has been the subject. Imagine a voiceless people living in a region where everything had a velvety surface, and who were thus deprived of all opportunity of experiencing what sound is. They could observe the slow pulsations of the air caused by their movements, and, arguing from analogy, they would no doubt infer that more rapid vibrations were possible. From the theoretical side, they could determine all about these more rapid vibrations. They merely differ, they would say, from slower ones by the number that occur in a given time. There is a merely formal difference. But suppose they were to take the trouble, go to the pains of producing these more rapid vibrations, then a totally new sensation would fall on their rudimentary ears. Probably at first they would only be dimly conscious of sound, but even from the first they would become aware that a merely formal difference, a mere difference in point of number in this particular respect, made a great difference practically as related to them, and to us the difference between 3 and 4 dimensions is merely formal, numerical. We can tell formally all about 4 dimensions, calculate the relations that would exist, but that the difference is merely formal does not prove that it is a futile and empty task to present to ourselves, as closely as we can, the phenomena of 4 dimensions. In our formal knowledge of it, the whole question of its actual relation to us, as we are, is left in abeyance. Possibly, a new apprehension of nature may come to us through the practical, as distinguished from the mathematical and formal, study of 4 dimensions. As a child handles and examines the objects with which he comes in contact, so we can mentally handle and examine 4-dimensional objects. The point to be determined is this: do we find something cognate and natural to our faculties, or are we merely building up an artificial presentation of a scheme only formally possible, conceivable, but which has no real connection with any existing or possible experience? This, it seems to me, is a question which can only be settled by actually trying. This practical attempt is the logical and direct continuation of the experiment Plato devised in the Meno. Why do we think true? Why, by our processes of thought, can we predict what will happen and correctly conjecture the constitution of the things around us? This is a problem which every modern philosopher has considered, and of which Descartes, Leibniz, Kant, to name a few, have given memorable solutions. Plato was the first to suggest it, and as he had the unique position of being the first deviser of the problem, so his solution is the most unique. Later philosophers have talked about consciousness and its laws, sensations, categories, but Plato never used such words. Consciousness, apart from a conscious being, meant nothing to him. His was always an objective search. He made man's intuitions the basis of a new kind of natural history. In a few simple words, Plato puts us in an attitude with regard to psychic phenomena, the mind, the ego, what we are, which is analogous to the attitude scientific men of the present day have with regard to the phenomena of outward nature. Behind this first apprehension of ours of nature there is an infinite depth to be learned and known. Plato said that behind the phenomena of mind that Meno's slave boy exhibited, there was a vast, an infinite perspective, and his singularity, his originality, comes out most strongly marked in this, that the perspective, the complex phenomena beyond, were, according to him, phenomena of personal experience. A footprint in the sand means a man to a being that has the conception of a man. But to a creature that has no such conception, it means a curious mark, somehow resulting from the concatenation of ordinary occurrences. Such a being would attempt merely to explain how causes known to him could so coincide as to produce such a result. He would not recognize its significance. Plato introduced the conception which made a new kind of natural history possible. He said that Meno's slave boy thought true about things he had never learned, because his soul had experience. I know this will sound absurd to some people, and it flies straight in the face of the maxim that explanation consists in showing how an effect depends on simple causes. But what a mistaken maxim that is! Can any single instance be shown of a simple cause? Take the behaviour of spheres, for instance, say those ivory spheres, billiard balls, for example. We can explain their behaviour by supposing they are homogeneous elastic solids. We can give formulae which will account for their movements in every variety. But are they homogeneous elastic solids? No, certainly not. They are complex in physical and molecular structure, and atoms and ions beyond open an endless vista. Our simple explanation is false, false as it can be. The balls act as if they were homogeneous elastic spheres. There is a statistical simplicity in the resultant of very complex conditions, which makes that artificial conception useful. But its usefulness must not blind us to the fact that it is artificial. If we really look deep into nature, we find a much greater complexity than we at first suspect. And so behind this simple I, this myself, is there not a parallel complexity? Plato's soul would be quite acceptable to a large class of thinkers if by soul and the complexity he attributes to it he meant the product of a long course of evolutionary changes, whereby simple forms of living matter, endowed with rudimentary sensation, had gradually developed into fully conscious beings. But Plato does not mean by soul a being of such a kind. His soul is a being whose faculties are clogged by its bodily environment, or at least hampered by the difficulty of directing its bodily frame, a being which is essentially higher than the account it gives of itself through its organs. At the same time, Plato's soul is not incorporeal. It is a real being with a real experience. The question of whether Plato had the conception of non-spatial existence has been much discussed. The verdict is, I believe, that even his ideas were conceived by him as beings in space, or, as we should say, real. Plato's attitude is that of science, inasmuch as he thinks of a world in space. But granting this, it cannot be denied that there is a fundamental divergence between Plato's conception and the evolutionary theory, and also an absolute divergence between his conception and the genetic account of the origin of the human faculties. The functions and capacities of Plato's soul are not derived by the interaction of the body and its environment. Plato was engaged on a variety of problems, and his religious and ethical thoughts were so keen and fertile that the experimental investigation of his soul appears involved with many other motives. In one passage, Plato will combine matter of thought of all kinds and from all sources, overlapping, interrunning, and in no case is he more involved and rich than in this question of the soul. In fact, I wish there were two words. One, denoting that being, corporeal and real, but with higher faculties than we manifest in our bodily actions, which is to be taken as the subject of experimental investigation, and the other word, denoting soul, in the sense in which it is made the recipient and the promise of so much that men desire. It is the soul in the former sense that I wish to investigate, and in a limited sphere only. I wish to find out, in continuation of the experiment in the Meno, what the soul in us thinks about extension, experimenting on the grounds laid down by Plato. He made, to state the matter briefly, the hypothesis with regard to the thinking power of a being in us, a soul. This soul is not accessible to observation by sight or touch, but it can be observed by its functions. It is the object of a new kind of natural history, the materials for constructing which lie in what it is natural to us to think. With Plato, thought was a very wide-reaching term, but still I would claim in his general plan of procedure a place for the particular question of extension. The problem comes to be, what is it natural to us to think about matter qua extended? First of all, I find that the ordinary intuition of any simple object is extremely imperfect. Take a block of differently marked cubes, for instance, and become acquainted with them in their positions. You may think you know them quite well, but when you turn them round, rotate the block round a diagonal, for instance, you will find that you have lost track of the individuals in their new positions. You can mentally construct the block in its new position by a rule, by taking the remembered sequences, but you don't know it intuitively. By observation of a block of cubes in various positions, and very expeditiously by a use of space names applied to the cubes in their different presentations, it is possible to get an intuitive knowledge of the block of cubes which is not disturbed by any displacement. Now, with regard to this intuition, we moderns would say that I had formed it by my tactual visual experiences, aided by hereditary predisposition. Plato would say that the soul had been stimulated to recognize an instance of shape which it knew. Plato would consider the operation of learning merely as a stimulus, we as completely accounting for the result. The latter is the more common sense view, but on the other hand it presupposes the generation of experience from physical changes. The world of sentient experience, according to the modern view, is closed and limited. Only the physical world is ample and large and of ever-to-be-discovered complexity. Plato's world of soul, on the other hand, is at least as large and ample as the world of things. Let us now try a crucial experiment. Can I form an intuition of a four-dimensional object? Such an object is not given in the physical range of my sense contacts. All I can do is to present to myself the sequences of solids which would mean the presentation to me under my conditions of a four-dimensional object. All I can do is to visualize and tactualize different series of solids which are alternative sets of sectional views of a four-dimensional shape. If now, on presenting these sequences, I find a power in me of intuitively passing from one of these sets of sequences to another, of being given one, intuitively constructing another, not using a rule but directly apprehending it, then I have found a new fact about my soul, that it has a four-dimensional experience. I have observed it by a function it has. I do not like to speak positively, for I might occasion a loss of time on the part of others if, as may very well be, I am mistaken. But for my own part, I think there are indications of such an intuition. From the results of my experiments, I adopt the hypothesis that that which thinks in us has an ample experience, of which the intuitions we use in dealing with the world of real objects are a part, of which experience the intuition of four-dimensional forms and motions is also a part. The process we are engaged in intellectually is the reading the obscure signals of our nerves into a world of reality by means of intuitions derived from the inner experience. The image I form is as follows. Imagine the captain of a modern battleship directing its course. He has his charts before him. He is in communication with his associates and subordinates, can convey his messages and commands to every part of the ship, and receive information from the conning tower and the engine room. Now, suppose the captain, immersed in the problem of the navigation of his ship over the ocean, to have so absorbed himself in the problem of the direction of his craft over the plain surface of the sea that he forgets himself. All that occupies his attention is the kind of movement that his ship makes. The operations by which that movement is produced have sunk below the threshold of his consciousness. His own actions, by which he pushes the buttons, gives the orders, are so familiar as to be automatic. His mind is on the motion of the ship as a whole. In such a case, we can imagine that he identifies himself with his ship. All that enters his conscious thought is the direction of its movement over the plain surface of the ocean. Such is the relation, as I imagine it, of the soul to the body. A relation which we can imagine as existing momentarily in the case of the captain is the normal one in the case of the soul with its craft. As the captain is capable of a kind of movement, an amplitude of motion, which does not enter into his thoughts with regard to the directing the ship over the plain surface of the ocean, so the soul is capable of a kind of movement, has an amplitude of motion, which is not used in its task of directing the body in the three-dimensional region in which the body's activity lies. If for any reason it becomes necessary for the captain to consider three-dimensional motions with regard to his ship, it would not be difficult for him to gain the materials for thinking about such motions. All he has to do is to call his own intimate experience into play. As far as the navigation of the ship, however, is concerned, he is not obliged to call on such experience. The ship as a whole simply moves on a surface. The problem of three-dimensional movement does not ordinarily concern its steering. And thus, with regard to ourselves, all those movements and activities which characterize our bodily organs are three-dimensional. We never need to consider the ampler movements. But we do more than use the movements of our body to effect our aims by direct means. We have now come to the pass when we act indirectly on nature, when we call processes into play which lie beyond the reach of any explanation we can give by the kind of thought which has been sufficient for the steering of our craft as a whole. When we come to the problem of what goes on in the minute, and apply ourselves to the mechanism of the minute, we find our habitual conceptions inadequate. The captain in us must wake up to his own intimate nature, realise those functions of movement which are his own, and in virtue of his knowledge of them, apprehend how to deal with the problems he has come to. Think of the history of man. When has there been a time in which his thoughts of form and movement were not exclusively of such varieties as were adapted for his bodily performance? We have never had a demand to conceive what our own most intimate powers are, but just as little as by immersing himself in the steering of his ship over the plain surface of the ocean, a captain can loose the faculty of thinking about what he actually does, so little can the soul loose its own nature. It can be roused to an intuition that is not derived from the experience which the senses give. All that is necessary is to present some few of those appearances which, while inconsistent with three-dimensional matter, are yet consistent with our formal knowledge of four-dimensional matter, in order for the soul to wake up, and not begin to learn, but of its own intimate feeling, fill up the gaps in the presentiment, grasp the full orb of possibilities from the isolated points presented to it. In relation to this question of our perceptions, let me suggest another illustration, not taking it too seriously, only propounding it to exhibit the possibilities in a broad and general way. In the heavens, amongst the multitude of stars, there are some which, when the telescope is directed on them, seem not to be single stars, but to be split up into two. Regarding these twin stars through a spectroscope, an astronomer sees in each a spectrum of bands of colour and black lines. Comparing these spectrums with one another, he finds that there is a slight relative shifting of the dark lines, and from that shifting he knows that the stars are rotating round one another, and can tell their relative velocity with regard to the Earth. By means of his terrestrial physics, he reads this signal of the skies. This shifting of lines, the mere slight variation of a black line in a spectrum, is very unlike that which the astronomer knows it means. But it is probably much more like what it means than the signals which the nerves deliver are like the phenomena of the outer world. No picture of an object is conveyed through the nerves. No picture of motion, in the sense in which we postulate its existence, is conveyed through the nerves. The actual deliverances of which our consciousness takes account are probably identical for eye and ear, sight and touch. If, for a moment, I take the whole earth together and regard it as a sentient being, I find that the problem of its apprehension is a very complex one, and involves a long series of personal and physical events. Similarly, the problem of our apprehension is a very complex one. I only use this illustration to exhibit my meaning. It has this especial merit that, as the process of conscious apprehension takes place in our case in the minute, so, with regard to this earth being, the corresponding process takes place in what is relatively to it very minute. Now, Plato's view of a soul leads us to the hypothesis that that which we designate as an act of apprehension may be a very complex event, both physically and personally. He does not seek to explain what an intuition is. He makes it a basis from whence he sets out on a voyage of discovery. Knowledge means knowledge. He puts conscious being to account for conscious being. He makes an hypothesis of the kind that is so fertile in physical science, an hypothesis making no claim to finality, which marks out a vista of possible determination behind determination, like the hypothesis of space itself, the type of serviceable hypotheses. And above all, Plato's hypothesis is conducive to experiment. He gives the perspective in which real objects can be determined, and in our present inquiry we are making the simplest of all possible experiments. We are inquiring what is natural to the soul to think of matter as extended. Aristotle says we always use a phantasm in thinking, a phantasm of our corporeal senses, a visualization or a tactualization. But we can so modify that visualization or tactualization that it represents something not known by the senses. Do we, by that representation, wake up an intuition of the soul? Can we, by the presentation of these hypothetical forms that are the subject of our present discussion, wake ourselves up to higher intuitions? And can we explain the world around by a motion that we only know by our souls? Apart from all speculation, however, it seems to me that the interest of these four-dimensional shapes and motions is sufficient reason for studying them, and that they are the way by which we can grow into a fuller apprehension of the world as a concrete whole. End of section 28. Section 29 of The Fourth Dimension by Charles Howard Hinton. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Appendix 2. A Language of Space. Part 2. Space names. If the words written in the squares drawn in Figure 1 are used as the names of the squares in the positions in which they are placed, it is evident that a combination of these names will denote a figure composed of the designated squares. It is found to be most convenient to take as the initial square that marked with an asterisk, so that the directions of progression are towards the observer and to his right. The directions of progression, however, are arbitrary and can be chosen at will. Thus, et, at, it, an, al will denote a figure in the form of a cross composed of 5 squares. Here, by means of the double sequence EAI and NTL, it is possible to name a limited collection of space elements. The system can obviously be extended by using letter sequences of more members. But without introducing such a complexity, the principles of a space language can be exhibited, and a nomenclature obtained adequate to all the considerations of the preceding pages. Reader's note. In the remainder of this section, whether a letter is uppercase or lowercase will be denoted by a change in tone rather than repeated reader's note, end reader's note, end reader's note. 1. Extension. Call the large squares in Figure 2 by the name written in them. It is evident that each can be divided as shown in Figure 1. Then the small square marked 1 will be n lowercase in n uppercase E lowercase n, or n starting with uppercase E. The square marked 2 will be et lowercase in n starting with uppercase E, or enet starting with uppercase E, while the square marked 4 will be n lowercase in et or eten, both starting with uppercase E. Thus the square 5 will be called il, starting with uppercase I. This principle of extension can be applied in any number of dimensions. 2. Application to three-dimensional space. To name a three-dimensional collocation of cubes, take the upward direction first, secondly the direction towards the observer, thirdly the direction to his right hand. These form a word in which the first letter gives the place of the cube upwards, the second letter its place towards the observer, the third letter its place to the right. We have thus the following scheme, which represents the set of cubes of column 1, figure 101, page 165. Reader's note. Unnumbered illustration on page 261. End reader's note. We begin with the remote lowest cube at the left hand, where the asterisk is placed. This proves to be by far the most convenient origin to take for the normal system. Thus nen is a null cube, 10 a red cube on it, and len a null cube above 10. By using a more extended sequence of consonants and vowels, a larger set of cubes can be named. To name a four-dimensional block of tesseracts, it is simply necessary to prefix an E, an A, or an I to the cube names. Thus the tesseract blocks schematically represented on page 165, figure 101, are named as follows. Reader's note. An unnumbered illustration on page 262, consisting of a 3x3 square of 3x3 squares, each with a part word of 4 letters in it. End reader's note. Derivation of point, line, face, etc. names. The principle of derivation can be shown as follows. Reader's note. A second unnumbered illustration on page 262 consists of a 3x3 square, n, et, l in the top row, an, at, al in the second row, in, it, il in the third row. End reader's note. Taking the square of squares, the number of squares in it can be enlarged, and the whole kept the same size. Reader's note. Unnumbered illustration on page 263. A 4x4 square. First row, n, et, l. Second row, an, at, al. Third row, an, at, al. Fourth row, in, it, il. End reader's note. Compare figure 79, page 138, for instance, or the bottom layer of figure 84. Now use an initial S to denote the result of carrying this process on to a great extent, and we obtain the limit names, that is, the point, line, area names for a square. Sat is the whole interior. The corners are sen, sel, sin, sil, while the lines are san, sal, set, sit. Reader's note. Second unnumbered illustration on page 263. A single square, top left corner sen, centre of top side set, top right corner sel, centre of left side san, centre of square sat, centre of right side sal, bottom left corner sin, centre of bottom side sit, bottom right corner sil. End reader's note. I find that by the use of the initial S, these names come to be practically entirely disconnected with the systematic names for the square from which they are derived. They are easy to learn, and when learned can be used readily with the axes running in any direction. To derive the limit names for a four-dimensional rectangular figure like the tesseract is a simple extension of this process. These point, line, etc. names include those which apply to a cube, as will be evident on inspection of the first cube of the diagrams which follow. All that is necessary is to place an S before each of the names given for a tesseract block. We then obtain appellatives which, like the colour names on page 174, figure 103, apply to all the points, lines, faces, solids, and to the hypersolid of the tesseract. These names have the advantage over the colour marks that each point, line, etc. has its own individual name. In the diagrams I give the names corresponding to the positions shown in the coloured plate, or described on page 174. By comparing cubes 1, 2, 3 with the first row of cubes in the coloured plate, the systematic names of each of the points, lines, faces, etc. can be determined. The asterisk shows the origin from which the names run. These point, line, face, etc. names should be used in connection with the corresponding colours. The names should call up coloured images of the parts named in their right connection. It is found that a certain abbreviation adds vividness of distinction to these names. If the final en be dropped wherever it occurs, the system is improved. Thus, instead of senen, seten, selen, it is preferable to abbreviate to sen, set, sel, and also use san, sin for sanen, sinen. Reader's note: unnumbered illustrations on pages 264, 265 and 266. End reader's note. We can now name any section. Take, for example, the line in the first cube from senin to senel. We should call the line running from senin to senel, senin, senat, senel a line light yellow in colour with null points. Here senat is the name for all of the line except its ends. Using senat in this way does not mean that the line is the whole of senat, but what there is of it is senat. It is a part of the senat region. Thus also the triangle, which has its three vertices in senin, senel, selen, is named thus: area, setat; sides, setan, senat, setet; vertices, senin, senel, sel. The tetrahedron section of the tesseract can be thought of as a series of plane sections in the successive sections of the tesseract, shown in figure 114, page 191. In B0, the section is the one written above. In B1, the section is made by a plane which cuts the three edges from sanen, intermediate of their lengths, and thus will be area, satat; sides, satan, sanat, satet; vertices, sanan, sanet, sat. The sections in B2, B3 will be like the section in B1, but smaller. Finally, in B4, the section plane simply passes through the corner named sin. Hence, putting these sections together in their right relation, from the face setat, surrounded by the lines and points mentioned above, there run three faces, satan, sanat, satet, three lines, sanan, sanet, sat, and these faces and lines run to the point sin. Thus the tetrahedron is completely named. The octahedron section of the tesseract, which can be traced from figure 72, page 129, by extending the lines there drawn, is named front triangle, selin, selat, selel, setal, senil, setit, selin, with area setat. The sections between the front and rear triangle, of which one is shown in 1b, another in 2b, are thus named points and lines salan, salat, salet, satet, satel, satal, sanal, sanat, sanit, satit, satin, satan, salan. The rear triangle found in 3b by producing lines is sil, sitet, sinel, sinat, sinin, sitan, sil. The assemblage of sections constitute the solid body of the octahedron satat with triangular faces. The one from the line selat to the point sil, for instance, is named selin, selat, selel, salet, salat, salan, sil. The whole interior is salat. Shapes can easily be cut out of cardboard, which, when folded together, form not only the tetrahedron and the octahedron, but also samples of all the sections of the tesseract taken as it passes cornerwise through our space. To name and visualize with appropriate colours a series of these sections is an admirable exercise for obtaining familiarity with the subject. Extension and connection with numbers. By extending the letter sequence, it is, of course, possible to name a larger field. By using the limit names, the corners of each square can be named. Thus, n sen, an sen, etc. will be the names of the points nearest the origin in n and in an. A field of points of which each one is indefinitely small is given by the names written below. Reader's note: an unnumbered illustration on page 268 consists of a 3x3 square, each square containing a two-syllable word. Top row, n sen, et sen, el sen. Second row, an sen, at sen, al sen. Third row, in sen, it sen, il sen. End reader's note. The squares are shown in dotted lines. The names denote the points. These points are not mathematical points, but really minute areas. Instead of starting with a set of squares and naming them, we can start with a set of points. By an easily remembered convention, we can give names to such a region of points. Let the square names with a final E added denote the mathematical points at the corner of each square nearest the origin. We have then, reader's note, an unnumbered illustration on page 269 consists of a 3 by 3 square. The 3 columns of squares are numbered 0, 1 and 2 from the origin at top left, as are the 3 rows. First row, NE, ETE, LE. Second row, ANE, ATE, ALE. Third row, INE, ITE, ILE. End reader's note. For the set of mathematical points indicated. This system is really completely independent of the area system, and is connected with it merely for the purpose of facilitating the memory processes. The word ENE is pronounced like NE, with just sufficient attention to the final vowel to distinguish it from the word N. Now, connecting the numbers 0, 1, 2 with the sequence EAI, and also with the sequence NTL, we have a set of points named as with the numbers in a coordinate system. Thus, NE is 0, 0, ATE is 1, 1, ITE is 2, 1. To pass to the area system, the rule is that the name of the square is formed from the name of its point nearest to the origin by dropping the final E. By using a notation analogous to the decimal system, a larger field of points can be named. It remains to assign a letter sequence to the numbers from +0 to +9 and from -0 to -9 to obtain a system which can be used to denote both the usual coordinate system of mapping and a system of named squares. The names denoting the points all end with E. Those that denote squares end with a consonant. There are many considerations which must be attended to in extending the sequences to be used, such as uniqueness in the meaning of the words formed, ease of pronunciation, avoidance of awkward combinations. I drop S altogether from the consonant series and short U from the vowel series. It is convenient to have unsignificant letters at disposal. A double consonant like ST, for instance, can be referred to without giving it a local significance by calling it ust. I increase the number of vowels by considering a sound like ra to be a vowel, using, that is, the letter R as forming a compound vowel. The series is as follows. Consonants 0, +N, -Z, 1, +T, -D, 2, +L, -TH, 3, +P, -B, 4, +F, -V, 5, +SH, -M, 6, +K, -G, 7, +CH, -J, 8, +NT, -ND, 9, +ST, -SP. Vowels 0, +E, -ER, 1, +A, -O, 2, +I, -OO, 3, +EE, -IO, 4, +AE, -OE, 5, +AI, -IU, 6, +AR, -OR, 7, +RA, -RO, 8, +RI, -ROO, 9, +REE, -RIO. Pronunciation: E as in men, A as in man, I as in, EE as in between, AE as AY in may, AI as I in mine, AR as in art, ER as EAR in earth, O as in on, OO as OO in soon, IO as in clarion, OE as OA in oat, IU pronounced like U. To name a point such as 23, 41, it is considered as 3, 1 on from 20, 40, and is called I feet. It is the initial point of the square I feet of the area system. The preceding amplification of a space language has been introduced merely for the sake of completeness. As has already been said, 9 words and their combinations applied to a few simple models suffice for the purposes of our present inquiry. End of section 29. End of The Fourth Dimension by Charles Howard Hinton.